Close your eyes for a moment and try to picture this. Somewhere, right now, in the silent blackness between the stars, a sun is dying. It's not a quiet, gentle fade. It's a violent, catastrophic detonation. In a single, blinding flash, it unleashes more energy than our own sun will produce in its entire 10 billion-year lifetime. This is not science fiction. This is a phenomenon known as a gamma-ray burst, one of the most energetic explosions in the entire universe, and it's a cosmic event of such staggering power that it can momentarily outshine every single star in its host galaxy combined. These bursts are the universe's ultimate powerhouses, the titanic engines that forge the very elements that make up our world and, ultimately, us. Across the vast expanse of space, these violent and beautiful events are constantly reshaping the cosmos, seeding it with the building blocks for new solar systems and, potentially, new life, in a cycle of destruction and creation on a scale that is almost impossible for us to fully comprehend. This video is your front row ticket to witness these incredible cosmic spectacles. We are about to embark on a journey through 30 astonishing facts about the universe's most energetic explosions. We will travel from the brilliant death throes of supernova, where stars collapse in upon themselves in a brilliant fountain of light, to the even more colossal hypernova, events so powerful they are thought to birth the mysterious black holes that lurk in the hearts of galaxies. We will explore the shockwaves that ripple through nebulae, triggering the birth of new stars, and the mysterious, fleeting flashes of gamma rays that have puzzled astronomers for decades. This is a story written in fire and light, a narrative of cosmic violence that is as beautiful as it is terrifying, and it's a fundamental part of the story of our own existence. Every atom of oxygen you breathe, every particle of iron in your blood, was once forged in the heart of a star and then scattered across the galaxy in one of these magnificent explosions. So prepare to have your perspective on the universe permanently altered. We are about to dive deep into the science and the spectacle of these celestial fireworks, uncovering their secrets and understanding their profound role in the grand tapestry of the cosmos. This journey is not just about observing distant events, it's about connecting with the very processes that made our world possible. It's a reminder that we are not just living in the universe, but that the universe is, in a very real way, living within us. Get ready to explore the most extreme and energetic events that reality has to offer. To truly grasp the sheer power we're talking about, we first need to define what makes an explosion cosmic. On Earth, an explosion might level a city. In space, an energetic explosion is something that can reshape an entire galaxy. The scale of energy involved is almost beyond human comprehension. We measure it not in megatons of TNT, but in units called foes, where one foe is the energy output of a supernova. To put that in perspective, a single foe is equivalent to the total energy our sun will radiate over its entire 10 billion-year lifespan. Now imagine that incomprehensible amount of power being unleashed not over billions of years, but in a matter of seconds. That is the breathtaking, terrifying reality of a gamma-ray burst, where the energy release makes even a supernova look modest. These events are the universe's ultimate benchmarks for raw power. Broadly speaking, when astronomers talk about the most energetic cosmic explosions, they are typically referring to three primary cataclysms. The first, and perhaps the most famous, is the supernova. This is the spectacular death of a massive star when its core can no longer support its own immense weight and collapses in on itself in a fraction of a second. The resulting rebound shockwave blasts the star's outer layers into space at incredible speeds, creating an expanding cloud of incandescent gas that we see as a brilliant, temporary new star in the sky. This explosion seeds the surrounding space with heavy elements like iron, gold, and uranium. Then there are the kilonovae, which are even more exotic and recent discoveries. These occur not from a single star's death, but from the violent collision of two ultra-dense stellar corpses, neutron stars. When these city-sized objects, each more massive than our Sun, spiral into each other, they release a cataclysmic blast of energy and a shower of neutrons. This unique environment is a cosmic forge for the heaviest elements in the universe. Nearly all the gold and platinum in your jewelry and much of the radioactive elements used in medicine were likely created in such a kilonova event billions of years ago. And finally, we have the grand champions of cosmic violence, gamma-ray bursts. These are not merely explosions in the traditional sense, they are ultra-relativistic jets of concentrated energy. Think of a star collapsing directly into a black hole, and in its final moments, focusing its dying breath into two narrow beams of pure gamma-ray radiation. If a supernova is a massive, omnidirectional bomb, a gamma-ray burst is a cosmic laser cannon. The energy is so focused that if one were to occur within our galaxy, and we were unlucky enough to be in the path of the beam, the effects on Earth's atmosphere would be catastrophic. This is why understanding these events is not just an academic exercise. It's a matter of grasping the fundamental forces that both build and threaten the cosmos. Ultimately, these titanic events are far more than just spectacular light shows. They are the fundamental engines of cosmic evolution. The death of one generation of stars in these blasts spreads the essential ingredients for new stars, planets, and life itself across the galaxy. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the heart of a star and then scattered into the void by one of these immense explosions. We are quite literally the children of stars that lived and died violently long before our Sun was even born. But to truly understand the power of a supernova, you need to appreciate that not all stellar explosions are created equal. Astronomers actually classify them into distinct types, and the differences between them are as fundamental as the difference between a sparkler and a stick of dynamite. The two main families are Type I and Type Roman II, and the key to telling them apart lies in their light. Specifically, when scientists spread a supernova's light out into a spectrum, they look for one particular element, hydrogen. If the spectrum shows strong hydrogen lines, it's a Type Roman II. If those hydrogen lines are missing, it's a Type I. This simple observation points to a profoundly different origin story for each cataclysm. Let's start with the core collapse supernova, or Type Roman II. This is the classic dramatic end for a single massive star at least 8 times heavier than our Sun. For millions of years, this star has been a cosmic pressure cooker, fusing lighter elements into heavier ones in its core, building up a layered structure like an onion. At its heart, it eventually creates an iron core, but iron is ash. It cannot be fused to release more energy. So when the core grows too massive, the outward pressure from fusion stops and gravity wins in an instant. The core collapses at nearly a quarter the speed of light, crushing itself into an ultra-dense ball of neutrons or even a black hole. The outer layers of the star, with all their hydrogen, come crashing down onto this new, impossibly hard surface and rebound in a titanic shockwave that blasts the entire star apart. This is the explosion we see, a brilliant, hydrogen-rich fireball that signals the death of a giant. On the other side of the cosmic coin, we have Type Ia supernova. These are not the deaths of massive stars, but rather the resurrection of dead ones. They begin with a white dwarf, the Earth-sized, super-dense corpse of a star like our Sun. If this white dwarf is in a binary system with a companion star, it can slowly siphon material from its neighbor. Like a zombie feeding, it grows heavier and heavier. There is a critical threshold, a limit called the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. Once the white dwarf steals enough matter to cross this line, the pressure in its carbon and oxygen core becomes so unimaginably intense that it triggers a runaway thermonuclear fusion reaction. The entire white dwarf is incinerated from the inside out in a few seconds, completely unbinding itself in a flash of pure atomic fire. Because a white dwarf has long since shed its outer hydrogen layers, its explosion shows no hydrogen in its spectrum, giving us a clean type Ia signature. This fundamental difference in how they explode makes type Ia supernova uniquely valuable to science. Because they all detonate at almost the exact same mass, they all reach nearly the same peak brightness. Think of it like this: if you were looking at a row of identical light bulbs from a distance, you could actually figure out how far away each one was just by how dim it appeared. A bulb that's twice as far away will be 4 times dimmer. Type Ia supernova are the universe's ultimate standard candle light bulbs. By observing how bright they appear from Earth, astronomers can calculate their distance with incredible precision. It was by using these cosmic mile markers in the late 1990s that 2 competing teams of scientists made a Nobel Prize-winning discovery. The expansion of the universe is not slowing down as everyone expected, but is instead accelerating, driven by a mysterious force we now call dark energy. So, from the ashes of a detonated stellar corpse, we have gleaned one of the most profound and unsettling secrets of our cosmos. At the heart of every massive star's life is a relentless battle, a tug of war between 2 titanic forces. For millions or even billions of years, the immense gravity of the star's own mass tries to crush it into a tiny point. Pushing back is the tremendous outward pressure generated by nuclear fusion in its core. This fusion is the star's engine, smashing lighter atoms together to form heavier ones, and in the process releasing the light and heat that define its existence. This process builds the star's interior like a cosmic onion, with layers of successively heavier elements. In a star like our Sun, the fusion stops at helium, but in much more massive stars, the core becomes hot and dense enough to fuse helium into carbon, and then carbon into oxygen, neon, and silicon. Each new fuel burns faster than the last, creating a layered structure right up to the final, fateful element, iron. Here is the critical turning point, the moment iron becomes the stellar Grim Reaper. For all the elements fused before it, the process is exothermic. It releases more energy than it consumes. This released energy is the very pressure that holds the star up against its own gravity. But when silicon fuses to create iron, something fundamental changes. Fusing iron atoms together does not release energy. It actually requires an input of energy to proceed. It's like trying to start a fire with wet wood. Instead of the fire sustaining itself, you have to constantly add more energy just to keep it smoldering. So, in the star's core, the moment an iron nucleus is forged, it begins to siphon the star's vital energy rather than contributing to it. The star doesn't know this, of course. Its fusion factory continues relentlessly, building an iron core that grows larger and larger. This iron core is essentially ash, the final, inert product of the star's nuclear burning. It just sits there, mass increasing, until it reaches what's known as the Chandrasekhar limit, about 1.4 times the mass of our Sun. At this critical threshold, the electron degeneracy pressure that was supporting the core, a quantum mechanical force, can no longer hold out against the crushing weight of the overlying star. The core's own gravity wins. In less than a single second, this city-sized iron core, which once represented the pinnacle of the star's achievement, catastrophically implodes. It collapses inward at speeds approaching 1/4 the speed of light. What happens next is almost incomprehensible. The core collapses all the way down until the protons and electrons are squeezed together to form a solid ball of neutrons, creating an object so dense that a single teaspoonful would weigh billions of tons. The outer layers of the star, which were rushing inward at hypersonic speeds, suddenly slam into this newly formed, impossibly hard neutron star surface. The inward collapse rebounds in an instant into a mighty outward moving shockwave. This shockwave, combined with a flood of neutrinos that carry away a colossal amount of energy, blasts the entire star apart from the inside out. The supernova explosion that results is so brilliant it can, for a few weeks, outshine its entire host galaxy. In that violent, fiery death, the star scatters all the elements it created throughout its life, including the iron from its doomed core, back into the cosmos. This iron, the very element that signaled the star's end, now becomes a building block for future worlds and potentially for future life. The Grim Reaper, in its final act, becomes a sower of seeds. That city-sized ball of neutrons left behind by the core collapse is one of the most bizarre objects in the universe, a neutron star. Imagine taking a star more massive than our Sun, with all of that incredible weight, and crushing it down into a sphere no wider than a large city like Manhattan. The density this creates is simply beyond human imagination. To put it in perspective, a single teaspoon of neutron star material would weigh not just millions but billions of tons here on Earth. That's the equivalent of compressing every single person on our entire planet into a single sugar cube of matter. Under that immense pressure, the very nature of matter changes. Electrons are forced into protons, creating a sea of neutrons so tightly packed that the star's surface is 1 billion times stronger than steel. It is, for all intents and purposes, a single, gigantic atomic nucleus. Now take this impossibly dense, collapsed star and set it spinning. A fundamental law of physics, the conservation of angular momentum, tells us that if a large, rotating object suddenly shrinks, it will spin much, much faster. Think of an ice skater pulling their arms in during a spin. They rotate more quickly. The parent star might have rotated once every few weeks, but when its core collapses from a sprawling sphere into that tiny city, its rotation rate skyrockets. The newborn neutron star can be spun up to dizzying speeds, completing multiple full rotations every single second. This is where the cosmic magic really begins. These stars often possess unimaginably powerful magnetic fields, trillions of times stronger than Earth's. This combination of rapid spin and intense magnetism acts like a cosmic dynamo, accelerating charged particles to near light speed at the star's magnetic poles. This process creates one of the most iconic phenomena in astronomy, the pulsar. As the neutron star spins, these beams of radiation, often radio waves but also light, X-rays and gamma rays, shoot out from its magnetic poles. If the magnetic axis is tilted compared to the rotation axis, these beams sweep through space like the blazing beams of a galactic lighthouse. From our perspective on Earth, if one of those beams happens to sweep across our line of sight once per rotation, we detect a regular pulse of energy. This is why they are called pulsars, short for pulsating stars. They are not actually stars pulsing in and out. They are spinning neutron stars, and we only see a flash each time the lighthouse beam points in our direction. The precision of these pulses is astounding, rivaling the accuracy of atomic clocks. For decades, these cosmic lighthouses have served as invaluable tools for testing the laws of physics in extreme conditions. The discovery of the first pulsar is a story that perfectly blends scientific rigor with a thrilling dash of science fiction. In 1967, a young PhD student at the University of Cambridge named Jocelyn Bell Burnell was analyzing data from a new radio telescope she had helped build. She noticed a peculiar, repeating signal in her chart recordings, a series of sharp, regular pulses arriving precisely every 1.337 seconds. The signal was so perfectly periodic and artificial, seeming that she and her supervisor, Anthony Hewish, half-jokingly labeled it LGM-1 for little green men. It was a serious, if unsettling, possibility at the time that they had stumbled upon a beacon from an advanced extraterrestrial civilization. The idea of an interstellar lighthouse built by aliens was a captivating, if not terrifying, explanation. After months of intense and secretive investigation, they managed to rule out terrestrial interference and, crucially, found a second, similar signal coming from a different part of the sky. This was the key. It was highly unlikely that two separate alien civilizations would be sending signals to a small, watery planet like Earth at the same time. The explanation had to be a natural, albeit previously unknown, astrophysical phenomenon. The object was soon identified as a rapidly spinning neutron star, the first pulsar ever detected. This monumental discovery, which earned Anthony Hewish a Nobel Prize award that controversially overlooked Jocelyn Bell Burnell's crucial role, opened an entirely new window into the study of extreme states of matter. It was a powerful reminder that the universe is often stranger and more wonderful than our wildest fiction, hiding its greatest secrets in the rhythmic heartbeat of a stellar corpse. But if a single neutron star is a marvel of cosmic density, then the collision of two of them is one of the most spectacular and consequential events in the universe. This cosmic cataclysm is known as a kilonova, and it represents a completely different kind of explosion from the supernova we've discussed. While a supernova marks the death of one massive star, a kilonova is the violent merger of two stellar corpses. For billions of years, a pair of neutron stars can orbit each other in a slow, decaying dance, losing energy in the form of gravitational waves, ripples in the very fabric of space-time. As they lose energy, they spiral closer and closer together, and in the final moments before impact, they whip around each other thousands of times per second. When they finally collide, the event is so immensely powerful that it doesn't just create a flash of light. It literally shakes the universe, sending out a detectable tremor in space-time itself. The historic confirmation of this phenomenon came in August of 2017, in a watershed moment for astronomy. For the first time, observatories on Earth detected the ripples of a gravitational wave event, and just 2 seconds later, the Fermi Space Telescope observed a short gamma-ray burst coming from the same patch of sky. This was the clue that sent telescopes all over the world and in space swiveling to that point. What they witnessed was the first multi-messenger observation of a cosmic event, combining the sense of touch from gravitational waves with the sense of sight from every part of the electromagnetic spectrum. The source was the collision of two neutron stars, 130 million light-years away in a galaxy called NGC 4993. The data painted a complete picture. The gravitational waves signaled the violent merger, the gamma-ray burst was the initial jet of energy, and the subsequent days-long glow was the kilonova itself, an explosion that fundamentally changed our understanding of where the heaviest elements in the cosmos come from. During the collision itself, the extreme conditions are unlike anything else. The intense gravitational and nuclear forces tear the two neutron stars apart, blasting a small but incredibly dense cloud of neutron-rich material into the surrounding space. In this expanding cloud, a frantic process known as rapid neutron capture, or the R process, occurs. Atomic nuclei are bombarded by a flood of free neutrons, allowing them to grow in size almost instantaneously, skipping past stable forms to create the heaviest and most exotic elements in the periodic table. This is the universe's primary forge for elements like gold, platinum, iodine, and even uranium. In that single event in 2017, astronomers calculated that the kilonova produced an amount of gold alone equivalent to many times the mass of our entire planet. Every gold ring, every platinum wedding band, and every trace of radioactive elements used in medical imaging on Earth was almost certainly created in a similar cataclysm billions of years ago, before our own solar system even formed. This creation process leaves a very distinct calling card. Unlike the brilliant blue-white light of a supernova, a kilonova has a unique and rapidly evolving reddish glow. The reason for this color is tied directly to the elements it creates. The cloud of material ejected from the merger is incredibly hot and expands rapidly. The heavy elements within it, like gold and platinum, are unstable and undergo radioactive decay. This decay releases energy, but the specific elements and the composition of the cloud cause it to absorb the bluer wavelengths of light and preferentially emit the redder ones. It's this radioactive glow of newly synthesized heavy elements that gives the kilonova its name and its characteristic ruddy hue, a cosmic signature that tells astronomers they are witnessing the literal birth of elements we consider precious. This event is the ultimate alchemy, transforming the remnants of dead stars into the very materials that have driven human civilization, commerce, and adornment for millennia. While the death of a star 8 times the mass of our Sun is a spectacular supernova, we must now turn our attention to the true titans of stellar destruction. For stars born with a truly monstrous mass, we're talking about 40, 50, or even more than 100 times the mass of the Sun. Their demise is not a supernova, but something far more extreme, a hypernova. The prefix hyper is not an exaggeration. These are explosions that can be up to 100 times more energetic than their already incredible supernova cousins. A hypernova is a stellar catastrophe on a scale that pushes the very limits of physics, and at its heart lies one of the most formidable objects in the universe, a newborn black hole. The key to understanding a hypernova lies in the collapsar model. In a typical core collapse supernova, the star's iron core implodes and forms a neutron star, and the rebound shockwave blasts the rest of the star apart. But in a hypernova scenario, the progenitor star is so unimaginably massive and its core so heavy that even a neutron star cannot withstand the gravitational onslaught. There is no rebound, no second chance. The core's collapse does not stop at the neutron star stage. It continues its catastrophic inward plunge, crushing itself past any known form of matter and directly forming a black hole. The entire core, in essence, vanishes from our observable universe, leaving behind only its immense gravitational pull. This is where the story diverges from a simple, spherical explosion. As the stellar material from the outer layers cascades down toward this newly formed black hole, it doesn't just fall in neatly. It forms an incredibly hot, swirling, and dense disk of material called an accretion disk, whirling around the black hole's event horizon at Chinese letter light speeds. The physics of this chaotic system, combined with the black hole's powerful rotation, acts like a cosmic particle accelerator. It focuses and channels a tremendous amount of energy into two narrow, opposing jets that scream outward from the star's poles at velocities exceeding 99.9% of the speed of light. These are not mere beams of light. They are ultra-relativistic jets of plasma and radiation, and they drill their way through the collapsing star like a cosmic blowtorch. It is these jets that provide the crucial link to one of the universe's greatest mysteries. When one of those incredibly focused jets is pointed fortuitously in the direction of Earth, we witness the most luminous electromagnetic event known to exist, a long-duration gamma-ray burst. The jet, finally breaking free from the stellar envelope, unleashes an initial pulse of gamma rays so concentrated and powerful that for those few seconds, it can outshine every star, every quasar, and every other source of light in the observable universe combined. The hypernova is the engine, and the gamma-ray burst is the brilliant, deadly spotlight it shines across the cosmos. This connection, established through decades of observation and theory, tells us that when we detect a long gamma-ray burst from a distant galaxy, we are likely witnessing the birth scream of a black hole from a collapsar, the final moment of a star so massive that its death is anything but ordinary. To put the sheer power of a hypernova into perspective, consider that the energy carried by those relativistic jets is often greater than the total energy released by the rest of the star's explosive disintegration. These events are so titanic that they are thought to be the primary source of the heaviest elements in the universe, beyond what a kilonova can produce, through processes even more extreme than the R process. A hypernova is more than just a bigger bang. It is a fundamental, directional, and universe-altering event. These explosions are so rare and so powerful that they are considered to be among the most energetic phenomena to have occurred since the Big Bang itself, serving as stark reminders that in the cosmos, the line between creation and destruction is often drawn by the most violent of forces. Now that we've explored the colossal engines behind these events, we arrive at the phenomenon itself, the gamma-ray burst, or GRB. These are not just explosions, they are the universe's most powerful and focused beams of pure energy, and they come in two distinct flavors, each with its own violent origin story. The key distinction astronomers use to classify them is surprisingly simple: duration. We separate them into long-duration gamma-ray bursts and short-duration gamma-ray bursts, a difference that points directly to two completely different cosmic catastrophes. Long-duration bursts are the true marathoners of the GRB world, typically lasting anywhere from 2 seconds to several minutes. Their source is the hypernova, the collapse of a truly massive star directly into a black hole. As we discussed during this collapse, the infalling material forms a swirling accretion disk around the newborn black hole, and powerful magnetic fields and rotational energy combine to launch two opposing jets of plasma and radiation. These jets, moving at over 99.9% the speed of light, must physically drill their way out through the outer layers of the dying star. This process takes time, and the duration of the gamma-ray flash we observe is essentially a timer for how long it takes the jet to fight its way to freedom. Once it breaks through, it screams into the void, and if Earth lies within the narrow cone of that jet's path, we witness a long-duration gamma-ray burst. For those few seconds, this single beam can momentarily outshine every other source of gamma rays in the entire observable universe. On the other side of the cosmic clock are the short-duration gamma-ray bursts. These are the sprinters, lasting less than 2 seconds, with most flashing for only a few hundred milliseconds. Their origin is not the death of a single massive star, but the spectacular merger of two neutron stars, the same event that produces a kilonova. In this incredibly violent dance, as the two ultra-dense objects spiral together and finally collide, they can also form a black hole surrounded by a temporary disk of debris. This system, for a fleeting instant, can also power a pair of relativistic jets. However, there is no massive stellar envelope for these jets to fight through. The energy is released almost instantly in a much shorter, sharper blast of gamma rays. This is the short GRB, a brilliant, ultra-short flash that signals the final embrace of two stellar corpses. What makes both types of bursts so incredibly luminous, far beyond a supernova, is the physics of these relativistic jets. The term relativistic comes from Einstein's theory of relativity, and it means the material in these jets is moving at a significant fraction of the speed of light. This near-light speed motion has a bizarre and powerful consequence called relativistic beaming. All of the energy that would normally be emitted in all directions gets compressed and focused intensely along the direction of travel. It's like the difference between a bare light bulb and a focused laser pointer. A supernova is like the light bulb, a brilliant but spherical explosion. A gamma-ray burst is the cosmic laser pointer. Its energy isn't spread out in a sphere but is concentrated into a narrow beam only a few degrees wide. This is why they appear so phenomenally bright to us, but only if we are looking directly down the barrel of the jet. For every one we see, there are hundreds pointed in other directions that we completely miss. The energy output in that beam is what truly bends the mind. Let's put some numbers to it. Our sun is a formidable powerhouse. Over its entire 10 billion-year lifespan, it will radiate a staggering amount of energy. Astronomers have calculated that a typical gamma-ray burst, in the span of just a few seconds, releases more energy in the form of gamma rays alone than our sun will over its entire life. To be clear, that is not more energy per second, that is more total energy, period. All of the sunshine that will ever fall on Earth, all of the light that has nurtured life for billions of years, is dwarfed by the output of a single GRB in a blink of an eye. And that's just the gamma rays. When you add in the energy carried by the jets themselves, the total can be hundreds of times larger still. This is energy on a scale that rivals the Big Bang itself for raw intensity, a reminder that the universe retains the capacity for violence on a scale that we are only just beginning to comprehend. With all this talk of cosmic power and distant cataclysms, it's natural to wonder what this means for us here on Earth. The sobering reality is that gamma-ray bursts are not just spectacular events for astronomers to observe, they are also potential existential threats. If a long-duration gamma-ray burst were to occur within our own Milky Way galaxy, and if its deadly jet were pointed directly at our planet, the consequences would be nothing short of an extinction-level event. The danger doesn't come from the explosion blowing us apart. The source would still be thousands of light years away. The true peril lies in the radiation itself. That concentrated beam of high-energy gamma rays would strike our atmosphere with the force of a nuclear bomb, detonating over every square mile of the planet's surface all at once. The immediate effects would be apocalyptic. The gamma-ray radiation would break apart the nitrogen and oxygen molecules in our upper atmosphere, initiating a complex chemical chain reaction that would ultimately destroy the ozone layer. This protective shield, which filters out the sun's harmful ultraviolet radiation, could be depleted by 50% or more in a matter of weeks, and it could take years or even decades to recover. Without this shield, the surface of the Earth would be bathed in lethal levels of UVB radiation. This would trigger a catastrophic collapse of the food chain, starting with the phytoplankton in the oceans that produce a significant portion of our oxygen and form the base of the marine ecosystem. Land plants would be severely damaged, and animals, including humans, would suffer from devastating radiation burns, increased rates of cancer, and widespread blindness. This isn't just a frightening thought experiment. There is a compelling scientific hypothesis that Earth may have already experienced such an event in its deep past. Around 440 million years ago, at the boundary between the Ordovician and Silurian geological periods, one of the Big Five mass extinctions occurred. The Ordovician extinction was particularly brutal to marine life, wiping out an estimated 85% of all species, and it happened in two distinct pulses separated by hundreds of thousands of years. While other causes like severe glaciation have been proposed, a gamma-ray burst remains a prime suspect for triggering this dual-phased catastrophe. The initial gamma-ray blast would have caused the immediate ozone depletion and UV damage, leading to the first wave of extinctions. The subsequent secondary effects, the dying plankton altering the atmosphere and the cooling of the planet from smog-like compounds formed in the upper atmosphere, could explain the second delayed pulse of death. Fossil records from the period show a pattern of die-off that fits this model disturbingly well. How vulnerable are we today? Statistically, the chance of a galaxy hosting GRB occurring close enough and being aimed precisely at Earth is extremely low. Astronomers estimate that a life-threatening burst from a nearby star might occur once every few hundred million years. The good news is that most of the massive stars that can produce long GRBs are located in distant, metal-rich regions of the galaxy, far from our solar system's position in a quieter spiral arm. However, the risk, however small, underscores a profound and humbling truth about our place in the cosmos. Our existence on this pale blue dot is contingent not just on local conditions, but on the stability and tranquility of our entire galactic neighborhood. A random stellar explosion thousands of light years away, a final flicker in our telescopic observations, could have ramifications that reach across the void and touch every living thing on our world. It is a powerful reminder that we are part of a dynamic and sometimes violent universe, a reality that connects our planetary fate directly to the life cycles of the stars. Even after the initial blinding flash of gamma rays fades to black, the story of a gamma ray burst is far from over. In many ways, it's just beginning. What follows that initial catastrophic detonation is a much longer, slower, and more revealing phase known as the afterglow. Think of it as the cosmic echo of the explosion, a fading fingerprint that lingers across the electromagnetic spectrum for days, weeks, or even months. This afterglow is not just a pretty light show, it is absolutely indispensable for astronomers, transforming a mysterious, impersonal flash in the dark into a detailed cosmic event with an address and a history. Without this lingering emission, gamma-ray bursts would remain enigmatic ghosts flickering in the void with no context or meaning. The afterglow gives them a voice, allowing scientists to listen to their story. The creation of this afterglow is a violent and dramatic process in its own right. Remember those ultra-relativistic jets screaming outward from the dying star or merging neutron stars at over 99.9% the speed of light. They don't travel through a perfect vacuum forever. Eventually, they plow into the thin soup of gas and dust that fills interstellar space, material that might have been shed by the progenitor star long before its death or simply the ambient medium of the galaxy. The collision is unimaginably violent. The leading edge of the jet acts like a cosmic snowplow, slamming into this material and creating a tremendous double-layered shockwave. This is the engine that powers the multi-wavelength afterglow we observe from Earth. This collision generates two distinct types of shock waves, each responsible for a different part of the light show. First, a forward shock plows outward into the undisturbed interstellar medium, violently heating and accelerating it. Simultaneously, a reverse shock can propagate back inward into the jet material itself. Within these chaotic, turbulent shock fronts, electrons are accelerated to near light speed and are then forced to spiral wildly around magnetic fields. This process, known as synchrotron radiation, is what generates the broad, lingering glow of the afterglow. It's the same basic physics as a particle accelerator here on Earth, but on a cosmic scale, and it produces light across every part of the spectrum, from radio waves all the way up to X-rays. The evolution of this light is what tells astronomers so much. Immediately after the gamma-ray flash, the afterglow is incredibly bright and energetic, often peaking in X-rays. As hours turn into days, the emission cascades down through the spectrum, becoming visible as optical light, and then eventually fading into the infrared and radio bands. It's like a cooling ember changing color as it loses energy. By meticulously observing this fading light curve across different wavelengths, scientists can piece together the energy of the original explosion, the density of the surrounding environment, and even the detailed geometry of the jet itself. It's forensic astronomy, using the clues left behind in this fading radiation to reconstruct the crime scene of a cosmic catastrophe. The single most important practical use of the afterglow, however, is triangulation. The initial gamma-ray burst detected by satellites like Swift or Fermi gives astronomers only a very rough idea of where to look, an area of the sky that could contain thousands of faint galaxies. But when the X-ray and optical afterglow appears, it provides a precise, point-like beacon. Ground-based telescopes, from large professional observatories to networks of automated robotic telescopes, can then swiftly swing into action, taking detailed images and, crucially, spectra of this fading point of light. The spectrum reveals the afterglow's redshift, a measure of how much the universe has expanded since the light left the burst, which directly tells us its distance. Furthermore, the precise location allows the Hubble Space Telescope or other powerful instruments to identify the faint, smudged shape of the host galaxy that the burst called home. It is this combination of precise location and measurable distance that has allowed us to confirm that gamma-ray bursts are not local phenomena, but truly cosmological events occurring in galaxies billions of light-years away, tracing the star-forming history of our universe across cosmic time. Moving from these theoretical models to a real-world event brings the science to life in a way nothing else can. and the story of supernova 1987 is one of the most important chapters in modern astronomy. On February 23, 1987, a brilliant new star appeared in the night sky over the southern hemisphere, exploding into view within the Large Magellanic Cloud, a small satellite galaxy of our own Milky Way located about 168,000 light-years away. It was the first supernova visible to the naked eye in over 380 years, since Kepler's star blazed in the sky in 1604. For astronomers, it was a once-in-several-lifetimes event, a cosmic gift happening not in a distant, unreachable galaxy, but right in our celestial backyard. Almost immediately, telescopes around the world and soon in space swiveled to observe this unprecedented event, initiating a campaign of observation that continues to this day and has fundamentally shaped our understanding of how massive stars die. The first and perhaps most profound confirmation from this event came not from light, but from nearly invisible particles called neutrinos. Just hours before the light from the explosion reached Earth, enormous underground detectors, one in Japan and another in the United States, recorded a brief but significant burst of 19 neutrinos. Now, neutrinos are ghostly subatomic particles that interact with matter so rarely they can pass through a light-year of lead without slowing down. But in the heart of a core collapse supernova, the formation of a neutron star produces a truly staggering flood of them, carrying away 99% of the star's gravitational energy. The detection of these 19 neutrinos, arriving from the direction of the Large Magellanic Cloud just before the light, was the smoking gun. It provided direct empirical evidence for the core collapse model. It confirmed that at the heart of this cataclysm, a neutron star had indeed just been born, and that the theoretical predictions about the sequence of a star's death were correct. This was multi-messenger astronomy in action decades before the term became common, using both particles and light to tell the complete story of a cosmic explosion. As the initial blaze of the supernova faded over subsequent weeks and months, the true legacy of 1987 began to unfold, revealing a complex structure that has made it a long-term natural laboratory. The progenitor star, a blue supergiant named Sanjalik 69°202, was known before it exploded, which gave astronomers a rare before and after picture. Then, as the light from the explosion itself faded, the Hubble Space Telescope revealed something astonishing: a set of 3 intricate rings of glowing gas encircling the site of the detonation like a cosmic bullseye. The central ring, a glowing hourglass-shaped structure of gas, is tilted toward us, while 2 larger, fainter outer rings loop above and below it. These were not created by the supernova itself. They were formed tens of thousands of years earlier when the progenitor star was in a slow, windy phase, shedding its outer layers. The supernova explosion then lit them up from the inside, like a flashbulb illuminating pre-existing smoke rings in a room. The evolution of these rings, particularly the central one, has provided a real-time physics lesson. The initial ultraviolet flash from the supernova heated the ring, causing it to glow brightly in visible light. Then, a few years later, the actual shockwave from the expanding supernova debris, traveling at thousands of kilometers per second, finally caught up with and slammed into this dense ring of gas. This collision, which began around 1996 and continues today, is like watching a slow-motion train wreck in space. The impact heats the ring material to millions of degrees, causing it to glow intensely in X-rays, and it has triggered the formation of millions of hotspots within the ring, each one a brilliant pinprick of new light. Observing this interaction has given astronomers an unprecedented view into how a supernova shockwave interacts with its pre-existing environment, how it transfers energy, and how it seeds the surrounding area with heavy elements. It's a detailed, decades-long case study of the aftermath of a stellar death, offering insights that no computer simulation could ever match on its own. While the dramatic brilliance of a supernova explosion fades after a few months, Its legacy endures for millennia in the form of a magnificent and ever-expanding cloud known as a supernova remnant. To witness this ongoing process, we need look no further than one of the most famous and studied objects in the sky, the Crab Nebula. This beautiful, filamentary cloud of gas and dust, located about 6,500 light-years away in the constellation Taurus, is the spectacular aftermath of a stellar cataclysm that was meticulously recorded by astronomers across the world in the year 1054 AD. Chinese and Arab stargazers and possibly Native American rock artists documented the appearance of a new star in the daytime sky, so brilliant it was visible for weeks and didn't fully fade from nighttime view for nearly 2 years. They were witnessing the death throes of a massive star, an event we now know as SN 1054. Today, nearly a millennium later, we can point our telescopes at that exact spot and see not a star, but a vast, chaotic nebula that is still violently expanding outwards, a cosmic crime scene that continues to reveal its secrets. The visual tapestry of the Crab Nebula is a direct result of that ancient explosion. What we see now is the shattered outer envelope of that star, blasted into space and racing outwards at speeds of around 1,500 kilometers per second. The intricate, web-like filaments that give the nebula its name are composed of the star's own material, primarily hydrogen and helium, now laced with heavier elements like oxygen, carbon, and iron that were forged in the star's core during its life and in the blast itself. These filaments glow for a fascinating reason. They are not just passively reflecting light, they are being energized by a powerful source of radiation from within. As the expanding shockwave plows into the surrounding interstellar medium, it also heats the gas to millions of degrees, causing it to emit X-rays, while the filaments themselves glow from a process called fluorescence, where their gases are excited by intense light. This creates a multi-wavelength portrait of cosmic violence, a beautiful testament to destruction. But the true heart of the Crab Nebula, the engine that keeps this entire structure brilliantly illuminated, is the tiny, incredibly dense object at its center, the Crab Pulsar. This is the collapsed core of the star that exploded over 9 centuries ago, a neutron star spinning at an astonishing 30 times per second. As it rotates, its powerful magnetic field, trillions of times stronger than Earth's, acts like a colossal dynamo, accelerating charged particles to nearly the speed of light. This generates a relentless, powerful wind that streams outward from the pulsar, filling the entire volume of the nebula and continuously injecting it with fresh energy. It is this pulsar wind, colliding with the slower-moving material from the ancient explosion, that creates a shimmering, bluish glow of synchrotron radiation across the nebula, making the Crab one of the brightest objects in the sky in radio waves and X-rays. The pulsar is literally powering its own memorial, a celestial ghost being given constant life by the spinning remnant of its own death. The role of the Crab Nebula and all supernova remnants like it extends far beyond being a beautiful cosmic monument. They are the primary recycling plants of the galaxy. For millions of years, the expanding shell of the remnant sweeps up vast quantities of the thin gas and dust that floats between the stars, gathering it like a cosmic snowplow. More importantly, it churns this material together with the newly forged heavy elements that were created in the progenitor star and during the supernova blast itself. Elements like iron, silicon, sulfur, and calcium are violently ejected and mixed into the interstellar medium. This process is fundamental to the chemical evolution of the galaxy. The pristine hydrogen and helium that filled the early universe could never form terrestrial planets or life on its own. It is only through the violent deaths of massive stars that space becomes seeded with these heavier atomic building blocks. This cosmic enrichment cycle is the ultimate source of our own existence. The cloud of gas and dust that collapsed to form our solar system over 4.5 billion years ago was not primordial. It was already enriched with the heavy elements from numerous generations of supernova that had exploded in our galactic neighborhood long before the Sun was born. Every atom of iron in the steel of a skyscraper, every atom of oxygen in the air we breathe, and every atom of calcium in our bones was once fused in the heart of a long-dead star and then scattered across light years by an explosion just like the one that created the Crab Nebula. We are not just living in the universe, we are literally made from the ashes of its most energetic explosions. The continuous study of supernova remnants allows us to trace this grand cycle of stellar birth, death, and rebirth, a cycle that turns cataclysmic destruction into the raw material for new stars, new planets, and potentially new life. But now, let's turn our attention to a stellar explosion so utterly violent and complete that it makes even a hypernova seem almost restrained. This is the Pair Instability Supernova, a detonation reserved for the true giants of the cosmos, stars born with a staggering mass between 130 and 250 times that of our Sun. In these colossal furnaces, gravity is so overwhelming and the core temperatures so unimaginably hot that the very physics of matter itself breaks down, triggering an explosion that doesn't just rip the star apart, it utterly and completely vaporizes it, leaving behind not even a ghost in the form of a black hole or neutron star. It is stellar annihilation on the grandest possible scale. The chain of events leading to this complete disintegration begins deep within the star's core as it fuses heavier and heavier elements. In a star of more normal mass, like the one that creates a regular core collapse supernova, the formation of an iron core signals the end. But in a pair instability supernova, the core is fusing oxygen. At the temperatures involved, which can soar into the billions of degrees, the photons buzzing around the core aren't just gentle light particles. They are packets of incredibly intense pure energy. When two of these high-energy gamma-ray photons collide with enough force, something truly remarkable happens. They spontaneously convert their energy into matter, creating a particle and its antimatter opposite, an electron and a positron. This process, known as pair production, is a direct consequence of Einstein's famous equation, E equals mc squared, demonstrating that energy and matter are two sides of the same coin. This spontaneous creation of matter, however, has a catastrophic consequence for the star. Those gamma-ray photons were the primary source of the outward radiation pressure that was helping the star hold itself up against its own immense gravity. When they vanish, converted into electron-positron pairs, that crucial supporting pressure suddenly drops. It's like instantly removing all the scaffolding from a massive building. Without that internal support, the core can no longer resist. The balance of power shifts entirely to gravity, which immediately and violently compresses the core, causing it to contract and heat up even further in a runaway feedback loop. This isn't a gentle collapse, it's a catastrophic implosion that raises the temperature to a point where oxygen fusion ignites almost everywhere at once. What follows is not a rebound shockwave, but a full-scale thermonuclear detonation. The entire core, rich with unburned oxygen, undergoes fusion simultaneously in an uncontrollable chain reaction. The energy released by this instantaneous oxygen fusion is so titanic that it doesn't just push back against the collapse, it overpowers the star's own gravity completely. There is no forming black hole, no compact remnant left behind. The entire star, from its core to its outermost layers, is completely and utterly blown to smithereens. Every single atom is blasted into the void in an expanding fireball of unprecedented power. A pair instability supernova is the ultimate expression of a star's self-destruction, a final act of violence so absolute that it erases itself from the universe entirely. Because these events require such a specific and enormous initial stellar mass, they are thought to be extremely rare in the modern universe. However, astronomers hypothesize that they were much more common in the very early universe, when the first generation of stars, known as population 3 stars, are believed to have formed from pristine hydrogen and helium and grown to these monstrous sizes. The discovery of modern candidates, like the extraordinarily bright supernova 2007 Bi, which shone with the luminosity of 100 billion suns at its peak, provides compelling evidence that these theoretical titans do indeed exist. The unique chemical signature they leave behind, a massive overabundance of certain elements and a complete absence of others, acts as a forensic fingerprint, allowing scientists to confirm that they have witnessed one of the most extreme and final acts a star can perform. If you thought the pair instability supernova was the final word on stellar destruction, prepare to venture into a realm of cosmic possibilities that pushes the very boundaries of known physics. We must now turn our attention to the most speculative and staggeringly powerful explosion ever conceived by theoretical science, the bosonova, also known as the Higgs instability supernova. This is not an event we have observed, nor is it one that is certain to even exist. Instead, it represents a fascinating and terrifying what-if scenario that emerges when we combine our understanding of the most massive stars with the most fundamental rules of the universe itself. To understand it, we need to delve into a concept that underpins all of reality, the Higgs field. Think of the universe not as empty space, but as being filled with an invisible, all-pervasive field of energy, much like an ocean. This is the Higgs field. Just as a fish moving through water experiences drag, particles moving through the Higgs field acquire what we perceive as mass. The interaction with this field is what gives different fundamental particles their distinct masses. An electron has a light mass because it interacts only weakly with the field, while a top quark is immensely heavy because it interacts with it very strongly. For decades, this was a theoretical cornerstone until the monumental confirmation of the Higgs boson at the Large Hadron Collider in 2012, which provided the crucial evidence that this field is real. Under normal conditions throughout the universe we observe, this field is stable, providing a consistent background that gives particles the mass we know and measure. Now imagine placing this stable, universal field under the most extreme conditions imaginable. The theoretical stage for a bosonova is a supermassive star, a true behemoth with a mass possibly exceeding 250 times that of our Sun. In the final, frenzied moments of such a star's life, as its core collapses under its own weight, the temperature and density can reach values so high they approach the energy scales of the very early universe, just fractions of a second after the Big Bang. At these incredible energy thresholds, something profound might happen to the Higgs field. According to some advanced models in particle physics, the Higgs field might not have just one stable state. It could be in what physicists call a false vacuum, a state that appears stable, like a ball resting in a small dip on the side of a large valley, but is not in its absolute most stable configuration. A Higgs instability supernova would be triggered if the core of this dying supergiant star provides the energy needed to push the Higgs field over that metaphorical hill, from its false vacuum into the true, absolute minimum of the valley. This transition would not be a gentle roll. It would be a catastrophic, fundamental restructuring of the very laws of physics in that location. In an instant, the Higgs field would drop to its true, lower energy state. This may sound benign, but the energy difference between the false vacuum and the true vacuum would be released in an unimaginable burst. More terrifyingly, in this new true vacuum bubble, the fundamental properties of particles would be different. The masses of quarks and electrons could change instantly, making the stable nuclear forces that hold atoms together simply cease to exist. The consequence of this instability would be far more than just an explosion. It would be a wave of true vacuum annihilation. The moment the true vacuum bubble forms in the star's core, it would begin expanding outward at nearly the speed of light. As this bubble expands, it would not just burn the star, it would effectively unmake it. Every atom, every proton and neutron it touched would instantly dissociate into a shower of fundamental particles as the laws of physics governing their stability were rewritten on the fly. The energy released from this phase transition of the entire star would be beyond any conventional measure. It would be an energy release not from nuclear fusion or gravitational collapse, but from the decay of the universe's very background energy field. The total energy yield could be so immense that it would temporarily outshine the combined light of every star in the observable universe, making even the brightest gamma ray burst appear as a faint candle in comparison. This speculative event sits at the thrilling intersection of cosmology and particle physics, a thought experiment that challenges our understanding of reality's fundamental stability. While the probability of such an event occurring in our contemporary universe is considered infinitesimally small, its theoretical existence serves as a powerful reminder that the universe may still hold violent potentials we have yet to witness. The study of such extremes pushes our scientific models to their limits, forcing us to ask profound questions about the nature of the vacuum of space and the ultimate fate of the cosmos itself. It represents the final frontier of stellar catastrophe, where a dying star does not just explode, but potentially triggers a chain reaction that could, in the most extreme and unlikely of scenarios, rewrite the laws of physics in its corner of the galaxy. Just when you thought neutron stars couldn't get any more extreme, nature presents us with the magnetar. If a typical neutron star is a cosmic cannonball, a magnetar is that same cannonball transformed into the most powerful magnet in the universe. These objects take the already intense magnetic fields of pulsars and amplify them to levels that are almost pure fantasy. We measure magnetic field strength in units called Gauss. A strong refrigerator magnet is about 100 Gauss. Earth's protective magnetic field is less than 1 Gauss. A typical neutron star can have a field of 1 trillion Gauss. But a magnetar, its magnetic field is a staggering 1,000 trillion Gauss. At that strength, the field is so powerful it becomes a tangible, lethal force. If you were to approach within 1,000 kilometers of a magnetar, its magnetic field would literally tear you apart, ripping the very atoms in your body asunder. It would erase the magnetic strip on your credit card from halfway to the moon. These unimaginable fields are thought to be generated in the chaotic first few seconds after a supernova, when the proto-neutron star is a seething, turbulent fluid of neutrons and protons. If this infant star is spinning fast enough, perhaps hundreds of times per second, its internal motions can act like a colossal dynamo, twisting and amplifying the magnetic field to these mind-boggling intensities. The energy stored in this magnetic prison is immense, and it places the entire star under incredible strain. The magnetar's solid crust, a crystalline lattice of iron nuclei 1 billion times stronger than steel, is constantly stressed and bent by the magnetic forces trapped beneath it. This sets the stage for one of the most violent events known, the starquake. Picture the crust of a neutron star not as a smooth, perfect sphere, but as a rigid, brittle shell under phenomenal pressure. As the magnetar's powerful magnetic field slowly evolves and shifts over time, it exerts stress on this crust, much like tectonic forces slowly bend the rocks along a fault line on Earth. The crust resists, storing this energy like a spring being compressed. Eventually, the strain becomes too great. The crust suddenly cracks and shifts, releasing its pent-up energy in a matter of milliseconds. This is a starquake, but on a neutron star, the scale is incomprehensible. A crustal shift of just 1 centimeter, a tiny crack by cosmic standards, releases more energy than the most powerful earthquake ever recorded on Earth. In fact, the energy released in a single, major starquake can exceed the total energy output of our Sun over 100,000 years. This sudden, catastrophic release of energy does not just create vibrations. It violently shakes the magnetar's entire magnetic field, which is frozen into its crust. The result is a giant flare. the magnetic field lines are snapped and reconfigured in an explosive event that accelerates protons and electrons to near light speed. These particles then interact with the intense magnetic field, emitting a brilliant, short-lived flash of radiation across the spectrum, but most powerfully in hard X-rays and gamma rays. For a fraction of a second, a single magnetar can outshine every other source of X-rays in the entire galaxy. It is a flash of pure magnetic fury, a testament to the titanic forces at play on the surface of a stellar corpse. We don't have to just imagine this, we have witnessed its power firsthand. On December 27, 2004, a wave of energy swept through our solar system from an object named SGR 1826, a magnetar located 50,000 light-years away in the constellation Sagittarius. In 0.2 of a second, it released a giant flare more energetic than any event ever recorded from outside our solar system. For that brief instant, this single object halfway across the Milky Way outshone the full moon. The gamma rays and X-rays that hit our planet were so intense that they actually ionized the upper layers of Earth's atmosphere, severely disrupting long-wave radio communications and expanding the ionosphere to a degree normally only seen during strong solar storms. Satellites orbiting Earth were momentarily blinded, their detectors driven into saturation by the intense flash. If this event had occurred from a source just 10 light-years away instead of 50,000, it could have severely damaged our ozone layer and potentially triggered a mass extinction. The 2004 event was a stark and humbling demonstration that even from across the galaxy, the death throes of a long-dead star can reach out and touch us, a reminder of our fragile place in a cosmos capable of violence on a scale we are only beginning to understand. Just when astronomers thought they had catalogued the universe's most violent outbursts, the cosmos revealed another surprise, a bizarre, new class of explosion that defies all existing categories. Known as fast blue optical transients, or FBOT for short, these cosmic flash in the pan events appear suddenly, shine with an intense blue light, and then fade away to almost nothing in a matter of days, rather than the weeks or months typical of supernova. Their discovery sent a jolt through the astronomical community, forcing a re-evaluation of what we thought was possible in stellar death. While a supernova might be like a brilliant firework that lingers in the sky, an FBOT is more like a lightning strike, a blinding, quick flash that leaves you wondering what exactly you just witnessed. The first of these enigmatic objects to gain widespread attention was an event catalogued as a 2018 cow, nicknamed the Cow, which was detected in June of 2018. It flared up in a galaxy 200 million light-years away, reaching peak brightness incredibly fast and then vanishing almost as quickly, all while emitting a distinctive, hot blue glow that set it completely apart from any known supernova. What makes FBOT so puzzling is that they don't fit neatly into any established box. They are not simply fast versions of other explosions, they represent something fundamentally different. For starters, their light curves are bizarre. A typical core collapse supernova takes weeks to rise to its maximum brightness as the expanding fireball grows and cools. An FBOT, by contrast, can achieve its blinding peak in just a few days. This suggests the explosion involves a much smaller amount of material, or perhaps a unique mechanism that releases its energy all at once. Furthermore, their spectra, the fingerprint of their chemical composition, are strangely featureless and overwhelmingly blue, indicating an extremely hot source with temperatures soaring to tens of thousands of degrees. This intense heat points to a physical process that is far more efficient at generating visible light than the radioactive decay of nickel that powers a standard supernova. It's as if the universe has a new, unknown type of stellar engine that we are only just beginning to recognize. The leading theories attempting to explain these strange events are as dramatic as the explosions themselves. One compelling idea is the failed supernova scenario involving a star often called a zombie star. In this model, a massive star undergoes a core collapse, but the outgoing shockwave doesn't have enough energy to successfully blast the star's outer layers into space. Instead, it stalls and the core forms a black hole. This newborn black hole then begins to violently feast on the star's own inner layers, which are now falling back onto it. The incredible gravitational energy released by this feeding frenzy is then channeled into a fast, hot, and brief outburst of light, an F-bot. It's a stellar death that doesn't quite succeed, leaving behind a black hole that immediately begins consuming its own progenitor. Another fascinating possibility involves stellar tides. Imagine a more common star like our Sun, wandering too close to a dormant black hole lurking in the center of its galaxy. The black hole's immense gravity would seize the star and tear it apart in a spectacular event known as a tidal disruption event. While we know these events happen, some astronomers suggest that a partial tidal disruption, where the black hole only strips away the star's outer envelope, could produce the unique, fast and blue signature of an F-bot. The shredded stellar material forms a bright, hot disk around the black hole, leading to a rapid and brilliant flare before the remaining stellar core is flung away on a new trajectory. This would be a death by 1,000 cuts rather than a single, final detonation. Perhaps the most exotic theory involves a special type of supernova interacting with dense material that was shed by the star just before its death. If a massive star ejected a dense shell of gas in the years or months leading up to its core collapse, then the subsequent supernova shockwave would slam into this shell at incredible speeds. The collision would convert the kinetic energy of the explosion into an intense, short-lived thermal flash, a brilliant pulse of blue light that rapidly cools as the shell expands and becomes transparent. This model elegantly explains both the speed and the color of F-bot, painting a picture of a star that essentially sets the stage for its own dramatic final act by preparing the environment around it. The ongoing mystery of fast blue optical transients serves as a powerful reminder that our map of the cosmos is still far from complete. With every new class of object we discover, we are humbled by the universe's boundless capacity for creativity and violence. These events challenge astrophysicists to develop new models and push the capabilities of our telescopes, from rapid response robotic observatories to powerful space-based instruments. Each new F-bot detected is another piece of a cosmic puzzle, guiding us toward a deeper understanding of the varied and dramatic ways that stars can end their lives. They represent the cutting edge of time-domain astronomy, proving that some of the most profound discoveries are not found in the steady, predictable heavens, but in the sudden, unpredictable flashes that illuminate the darkness for a fleeting moment. While magnetars release their fury from magnetic fields and supernova from gravitational collapse, there exists another cosmic cataclysm driven by gravity's pure, undistorted pull. Imagine a star much like our own Sun on a routine orbit through its galaxy. Its path through sheer cosmic chance takes it on a trajectory that brings it perilously close to the galaxy's central, supermassive black hole. Initially, the star feels only a gentle tug, but as it crosses a critical threshold known as the Roche limit, the black hole's gravitational grip becomes absolute. The force of gravity on the side of the star nearest the black hole is exponentially stronger than the force on the far side. This difference, known as a tidal force, begins to stretch the star. It is no longer a cohesive sphere, but an object being pulled apart in a cosmic tug-of-war it cannot possibly win. This is the beginning of a tidal disruption event, one of the most violent and dramatic spectacles in the universe. The star is progressively stretched into a long, thin stream of superheated gas, a process vividly nicknamed spaghettification. In a matter of hours, the entire stellar structure is completely shredded, its material drawn out into a vast, elliptical arc around the black hole. But the star's material isn't immediately swallowed. Instead, about half of it gets flung out into the darkness of interstellar space, while the other half settles into a frenzied, chaotic accretion disk, whirling around the event horizon at Chinese letter light speeds. It is this doomed material, superheated through friction and gravitational compression as it spirals inward, that creates the event's brilliant calling card, an enormous flare of radiation that can outshine every star in its host galaxy for months. What makes these events so valuable to science is what they reveal. The vast majority of supermassive black holes in the universe are dormant. They are not actively feeding on gas and dust and therefore emit very little light, making them nearly impossible to detect directly. A tidal disruption event acts like a cosmic flare gun, suddenly illuminating this dark monster and its immediate surroundings. By analyzing the light curve of the resulting flare, how quickly it brightens and how slowly it fades, astronomers can calculate the mass of the central black hole. The spectrum of the emitted light reveals the chemical composition of the devoured star, offering a unique biopsy of a solar system that no longer exists. In this way, a star's catastrophic death becomes a powerful tool, allowing us to census the population of hidden black holes that would otherwise lurk undetected in the hearts of galaxies, mapping the invisible architecture of the cosmos. This extraordinary journey from cosmic cataclysm to biological building block brings us to perhaps the most profound connection of all, the direct link between these stellar explosions and our own existence. Every time you take a breath, every time your heart beats, you are participating in a cycle that began billions of years ago inside stars that no longer exist. The popular phrase, "we are stardust," is not just a poetic metaphor, it is a literal scientific fact. Aside from the primordial hydrogen, which dates back to the Big Bang itself, nearly every single element that makes up our bodies and our world was forged in the nuclear furnaces of stars and then violently scattered across the galaxy by supernova, hypernova, and kilonova. Let's trace the journey of a single oxygen atom, one of the most crucial elements for life as we know it. Its story begins inside a massive star far more colossal than our Sun. For millions of years, this star fused hydrogen into helium in its core, but as it aged and the core contracted, the temperature soared to over 100 million degrees, hot enough to begin fusing helium atoms into carbon. In the final, frantic stages of the star's life, the temperature climbs even higher and the carbon itself begins to fuse, creating oxygen. This oxygen is trapped, locked in the onion-like layers of the dying star, destined to be incinerated or crushed into oblivion. Then the supernova occurs. The cataclysmic shockwave blasts through these layered shells, hurling the newly forged oxygen atoms outward at tremendous speeds, mixing them with other elements like carbon and nitrogen in an expanding cloud of incandescent gas. For eons, this oxygen atom drifts through the interstellar medium, a tiny part of a vast nebula, until the gravitational collapse of a new gas cloud, one enriched by countless previous supernovae, forms a new solar system. It becomes part of a forming planet, part of its oceans and atmosphere, and eventually part of the water molecule that would one day sustain the first stirrings of life. Now consider the iron in your blood, the element that gives hemoglobin its power to carry life-giving oxygen throughout your body. Iron holds a unique and ominous place in stellar physics. As we discussed, it is the ash of nuclear fusion, the element whose formation in a star's core signals its imminent death. That iron atom was created in the final moments of a massive star's life, just before the core collapsed. During the supernova explosion itself, the intense neutron flux can create even more iron through rapid capture processes. Once ejected, that iron atom, along with countless others, traveled across the galaxy. It was incorporated into the dust and gas that coalesced into our solar system 4.6 billion years ago, becoming a fundamental component of the planet Earth. Billions of years later, it was absorbed by plants and then by animals, eventually finding its way into the very bloodstream of a species that would one day gaze at the stars and wonder about its own origins. The same element that heralds a star's death is absolutely essential for our life. This cosmic recycling program extends to the most precious and rare elements as well. The gold in a wedding band, the platinum in a catalytic converter, or the iodine essential for your thyroid gland. These heavy elements cannot be forged in the ordinary fusion processes of a living star. They require something even more extreme. As we learned, these are the products of kilinovae, the spectacular collisions of neutron stars. In those violent mergers, a shower of neutrons bombards lighter atomic nuclei, building them up almost instantly into the heavy elements at the bottom of the periodic table. This material was then incorporated into the next generation of star formation, including the cloud that gave birth to our solar system. When you hold a piece of gold, you are holding a relic of one of the most violent and energetic events in the universe, an event that occurred perhaps billions of years before our sun was even born. This grand narrative connects us directly to the cosmos in the most intimate way possible. The calcium in our bones, the phosphorus in our DNA, the nitrogen in our very genes, all were synthesized in stars and distributed by their explosive deaths. Our planet, our bodies, and every living thing we see around us are composed of this recycled stellar material. We are not just inhabitants of the universe looking outward. We are the universe itself, become conscious and looking back at its own history. The carbon atoms in the cells of your hand could have once been part of a giant star that died in a brilliant supernova flash when the Earth was still a molten rock. The oxygen you just breathed might have traveled for millions of years through interstellar space before arriving here. This realization is one of the greatest triumphs of modern astronomy, a beautiful and humbling truth that binds our story inextricably to the life cycles of the stars. We are the universe's way of understanding itself, forged from the ashes of its most magnificent and destructive fireworks. For centuries, we've pictured a star's final explosion as a perfectly spherical blast, a beautiful, symmetrical fireball expanding evenly in all directions. This elegant simplicity, however, turns out to be more of a cosmic ideal than a reality. The truth is far more chaotic and interesting. Many, if not most, supernovae are profoundly asymmetric explosions. The star doesn't just pop like a uniform balloon, it detonates with a violent lopsidedness, and the consequences of this imbalance ripple across the galaxy, launching the corpses of dead stars on incredible journeys. This inherent wonkiness arises from the very heart of the explosion mechanism itself. While the core collapse might happen in a roughly spherical manner, the rebound of the shockwave is anything but. The interior of a massive star in its death throes is a seething, turbulent maelstrom. Vast convective bubbles like boiling water in a pot churn beneath the surface, and the intense neutrino-driven winds don't blow with perfect uniformity. This creates regions of higher and lower pressure, causing the rebounding shockwave to be nudged and distorted, punching its way out of the star more easily in one direction than in others. It's less like a perfect bubble and more like a cork finally shooting out of a bottle that's been shaken. This directional violence has a dramatic effect on the newborn compact object left behind, the neutron star. According to Newton's third law, for every action, there is an equal and opposite reaction. If a huge amount of stellar material is ejected preferentially in one direction, the neutron star will be kicked powerfully in the opposite direction, like a cannon recoiling after firing a cannonball. This is the supernova kick, and it can impart tremendous velocities to these stellar cinders. A typical kicked neutron star can be sent hurtling through space at hundreds of kilometers per second. To put that into perspective, at that speed, you could travel from the Earth to the Moon in less than half an hour. These kicks explain why we so often find neutron stars and pulsars far away from the galactic regions where massive stars are born. they have been unceremoniously booted out of their stellar nurseries and sent racing through the interstellar void. One of the most spectacular examples of this phenomenon is a pulsar known as PSRB 2224+65, which has earned the unforgettable nickname the Cosmic Cannonball. Discovered by the Chandra X-ray Observatory, this pulsar is not just moving quickly, it is traveling at a mind-boggling speed of over 3.5 million miles per hour. Behind it, it trails a brilliant 12-light-year-long tail of X-ray emission, a direct result of its supersonic travel through the thin interstellar gas, a cosmic wake marking its path. At this incredible velocity, the Cosmic Cannonball is not just on a joyride through the Milky Way, it is on an escape trajectory. The gravitational pull of our entire galaxy is not strong enough to hold onto it. In the distant future, this stellar remnant will break free from the Milky Way's grasp entirely and spend eternity drifting alone in the vast, dark emptiness of intergalactic space, a lone voyager cast out from its home. The existence of these high-velocity pulsars tells a deeper story about the supernova that created them. The immense force required to achieve such a kick points to an explosion of extreme asymmetry. For a neutron star to be accelerated to millions of miles per hour, the explosion that birthed it must have been profoundly lopsided, with a significant portion of the star's ejecta blasting out in a concentrated direction. This provides crucial observational evidence for the complex, messy, and multi-dimensional nature of core collapse physics. It shows us that the simple, spherical models are just a starting point, and that the real universe operates with a beautiful, chaotic complexity that can send the remnants of its dead stars screaming across the cosmos. At the core of our understanding of stellar fate lies a deceptively simple number, a precise threshold that separates a quiet, eternal fade from one of the most violent and useful explosions in the cosmos. This is the Chandrasekhar limit, approximately 1.4 times the mass of our Sun. It represents the maximum weight a white dwarf star can support against its own gravity. A white dwarf is the exposed, degenerate core of a star like our Sun, a fantastic object where matter is so densely packed that a single sugar cube of it would weigh as much as an elephant here on Earth. It's supported not by the heat of fusion, which has long since ceased, but by a quantum mechanical force called electron degeneracy pressure. The electrons within the star, forbidden from occupying the same quantum state, push back against the crushing force of gravity, creating a stable, Earth-sized ember that will slowly cool over billions of years. But this stability is conditional, entirely dependent on the star staying below that 1.4 solar mass line. The journey toward catastrophe for a white dwarf almost always involves a companion. Many stars in the universe are born in binary systems, and if a white dwarf has a nearby partner, a red giant or even a main sequence star, it can begin a process of cosmic theft. Its powerful gravity can slowly siphon hydrogen-rich gas from its neighbor. This stolen material doesn't just pile onto the surface, it accumulates, compresses, and heats up. Periodically, this layer of hydrogen becomes hot and dense enough to ignite in a runaway fusion flash, causing a smaller, recurrent explosion we observe as a nova. This outburst blasts some of the accumulated material back into space, but often, not all of it is lost. Over thousands of years, the white dwarf can persistently pull in more matter than it ejects, and its mass begins to creep gram by gram towards the ultimate tipping point. When the white dwarf's mass finally crosses the Chandrasekhar limit, the delicate quantum balance that has supported it for eons is shattered. Electron degeneracy pressure, which was once strong enough to hold up a star, is suddenly overwhelmed. The core, primarily composed of carbon and oxygen, is subjected to pressures and temperatures so extreme that a new, unstoppable type of fusion is triggered. This isn't the steady, stable fusion of a living star. It's a runaway thermonuclear inferno. Carbon fusion ignites almost simultaneously throughout the entire degenerate core. Because the core is degenerate, its pressure doesn't increase with temperature in the same way as in a normal gas. There is no stabilizing expansion to slow the reaction down. The fusion rate skyrockets, and in a matter of seconds, the entire white dwarf is incinerated from the inside out. The energy released is so vast that it completely unbinds the star, blasting it to pieces in a titanic explosion we classify as a Type Ia supernova. There is no remnant left behind, no neutron star, no black hole, just an expanding cloud of newly synthesized elements, rich with iron and radioactive nickel, racing outward into the galaxy. This specific and repeatable trigger mechanism is what makes Type Ia supernova so uniquely valuable to cosmology, because every single one of them detonates at almost the exact same mass, the Chandrasekhar limit. They all reach nearly the same intrinsic peak brightness. You can think of them as cosmic flashbulbs, each with the same wattage. If you see one flashbulb up close and another from a mile away, the more distant one will appear much dimmer. By measuring how dim a Type Ia supernova appears from our vantage point on Earth, astronomers can calculate its distance with remarkable precision. They are the gold standard for cosmic mile markers, the most reliable standard candles we have for measuring the vast scales of the universe. It was this very property that led to one of the most startling discoveries of the 20th century. In the late 1990s, two independent teams of astronomers were using distant Type Ia supernova to measure how much the expansion of the universe was slowing down due to gravity. To their profound shock, they found the opposite. The most distant supernova were fainter than expected, meaning they were farther away than anyone had predicted. The expansion of the universe wasn't slowing down, it was accelerating. This discovery, which earned the teams the Nobel Prize in 2011, pointed to the existence of a mysterious, repulsive force we now call dark energy, a force that makes up about 68% of the cosmos and is shaping the ultimate fate of everything. All of this was revealed by the precise, predictable detonation of white dwarf stars, a final act of stellar violence governed by a simple, critical number first calculated by a brilliant young physicist named Subrahmanyan Chandrasekhar. His work showed that even in death, the stars can provide the keys to unlocking the deepest secrets of the universe. Now, let's zoom in from that grand, galaxy-spanning legacy and peer into the very heart of the cataclysm itself, into the first catastrophic seconds when a star's fate is sealed. The core of a massive star, having built up an iron core the size of Earth but containing more mass than our entire Sun, has reached the end of the line. For just a moment, an eerie silence falls in the nuclear sense. Fusion stops, and the outward pressure that has supported the star for millions of years vanishes. In that instant, gravity, which has been patiently held at bay, wins the war. The core begins to implode, and what happens next is a sequence of events so rapid and violent it challenges the imagination. The entire city-sized iron core collapses inward at a quarter of the speed of light. In less than 1 second, it shrinks from a sphere thousands of miles across to a ball of neutrons just a dozen miles in diameter. This is the birth of the proto-neutron star, an object so dense that the space between its atoms is eliminated, crushing protons and electrons together to form a solid mass of neutrons. As this newborn neutron star forms, it does something extraordinary. It sends out a distress call, but not in the form of light or sound. It releases a blast of ghostly particles called neutrinos. These are among the most elusive fundamental particles in existence, able to pass through a light year of lead without a single interaction. But in the hellish density of the collapsing core, they are produced in such stupefying numbers that they become the dominant force. For a fraction of a second, a flood of neutrinos containing a significant portion of the star's total binding energy races outward from the core. This initial burst is so immense it briefly carries away more energy than all the stars in the observable universe combined. Meanwhile, the collapse of the core has created a vacuum, and the star's outer layers, which were once supported by the core, are now falling inward at hypersonic speeds. This entire mass of stellar material, all the hydrogen, helium, and heavier elements, plunges toward the new neutron star. It slams into its impossibly hard surface with the force of 1,000 suns, creating a mighty shockwave that rebounds outward. But this shockwave, born from the sheer impact of the collision, is initially too weak to overcome the relentless rain of infalling material. It stalls, becoming a standing accretion shock just a few hundred kilometers from the neutron star's surface. For a few critical milliseconds, the supernova is in peril of failing, of the entire star collapsing directly into a black hole without a spectacular explosion. This is where the neutrinos return as the unsung heroes of the apocalypse, that unimaginable flood of particles which initially raced out unimpeded, now encounters the incredibly dense material just outside the neutron star. Here, the neutrinos finally start to interact, depositing a fraction of their colossal energy into the stalled shockwave. It acts like a cosmic defibrillator, delivering a massive energy jolt directly behind the shock. This transfer of energy, known as the neutrino heating mechanism, revives the stalled shock. It begins to push outward again, but this time with renewed, unstoppable vigor. The shockwave starts to disrupt the orderly infall of the star's outer layers, creating a violently convective region where massive bubbles of hot plasma buoyantly rise, helping to further push the shock outward. This is the moment the star truly dies. The revived shockwave accelerates, and within a second, it becomes a detonation wave that will rip the entire star apart from the inside out, blasting its chemical richness into the interstellar medium. The incredible thing is, we have direct experimental proof that this neutrino-driven mechanism is correct, and it comes from that famous stellar neighbor, supernova 1987A. Just hours before the light from the explosion reached Earth, underground detectors in Japan and the United States recorded a brief, distinct burst of 19 neutrinos. These weren't just any random particles. Their energy and timing perfectly matched the predictions for a core collapse event. They were the direct messengers from the formation of the neutron star, arriving hours before the photons because they escaped unimpeded from the core the moment it collapsed, while the light had to wait for the shockwave to fight its way to the surface. This detection was the smoking gun, confirming that our theoretical understanding of those first frantic seconds was on the right track. It connected the invisible world of particle physics directly to the grandest explosions in the cosmos, proving that the ghostly neutrino plays the lead role in one of the universe's most dramatic acts of destruction and creation. But just when we thought we had supernova all figured out, the universe unveiled an even more brilliant class of stellar death. Imagine a supernova, already one of the most powerful explosions imaginable, and then multiply its brightness by 10, by 50, even 100 times. This isn't a theoretical exercise, it's the reality of superluminous supernova. These are cosmic beacons so intensely bright they can outshine entire galaxies for months, and their discovery has forced astronomers to completely rethink the limits of stellar explosions. While a typical core collapse supernova might peak at the brightness of several billion suns, a superluminous supernova can radiate with the power of over 100 billion suns, making them visible across vast cosmic distances and deep into the early universe. The search for the engine behind this staggering luminosity has led to several compelling and sometimes competing theories. The first and most straightforward explanation involves a truly immense quantity of a radioactive element, nickel-56. In a standard type Ia supernova, the decay of just a few tenths of the sun's mass of nickel powers the brilliant light curve. For a superluminous event, however, the thinking is that the explosion must produce a colossal amount of this radioactive material, sometimes the equivalent of several solar masses. As this nickel decays into cobalt and then into stable iron, it releases a torrent of gamma rays that heat the expanding debris, creating the phenomenal glow. It's like comparing a campfire to a massive industrial furnace. The basic fuel is similar, but the sheer scale of the fuel source creates an entirely different level of brilliance. However, the sheer energy demands of the brightest superluminous supernova push even the radioactive nickel model to its limits. This has led to the rise of a more exotic and dynamic explanation, the power of a newborn, rapidly spinning magneta. Picture the aftermath of a core collapse supernova. Instead of leaving behind a quietly cooling neutron star, the collapse results in a magneta, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's and spinning hundreds of times per second. This object is then embedded deep within the expanding cloud of stellar debris. The magneta's immense rotational energy, channeled by its unbelievable magnetic field, acts like a continuously running engine. It bombards the supernova ejector from the inside with a relentless wind of radiation and particles, effectively reheating the explosion for months or even years. This continuous energy injection can explain the sustained, extraordinary brightness that defines these events, acting as a cosmic battery that keeps the light show going long after a normal supernova would have begun to fade. This magneta model is particularly attractive because it provides a natural explanation for the unique light curves of many superluminous supernovae. They often don't just fade away smoothly, their brightness can plateau for a remarkably long time before finally beginning to dim, a signature that perfectly matches what you would expect from a central engine persistently pumping energy into the system. It's the difference between a flashbulb, which gives one brilliant pulse of light, and a lighthouse beacon, which shines continuously. The magneta provides that sustained, powerful beacon, illuminating its own funeral shroud with unparalleled intensity. The existence of these ultra-bright explosions is more than just a cosmic curiosity. It provides astronomers with an incredibly powerful tool for observational cosmology. Because superluminous supernovae are so intrinsically bright, they can be detected at much greater distances than their ordinary counterparts. This allows scientists to peer back further in time, observing the deaths of some of the universe's earliest generations of stars. By studying these events in distant galaxies, we can investigate the conditions of the early cosmos, measuring star formation rates and the metal enrichment of galaxies when the universe was only a fraction of its current age. They act as natural searchlights, illuminating cosmic history and helping us understand how the first massive stars lived and died, seeding the pristine early universe with the first heavy elements necessary for planets and life. But these stellar cataclysms don't occur in isolation. Their frequency and impact are profoundly shaped by their galactic neighborhoods. To understand the true role of cosmic explosions, we must zoom out from individual stars and look at the broader ecosystems they inhabit. This brings us to a fascinating class of objects known as green pea galaxies. Discovered by citizen scientists in the Galaxy Zoo project, these are small, compact galaxies that appear as tiny, round, and distinctly greenish blobs in telescopic images. Their unusual color is a direct clue to their nature. It comes from intensely glowing oxygen, a telltale sign of rampant star formation, and the powerful ultraviolet radiation blasting from countless newborn massive stars. These galaxies are essentially cosmic factories operating at a frenetic, almost unsustainable pace, churning out new stars at a rate that can be hundreds or even thousands of times greater than that of our own sedate Milky Way. Within these stellar nurseries on overdrive, the life cycle of stars is dramatically accelerated. Where our galaxy might produce a handful of supernova per century, a green pea galaxy is a constant fireworks display of stellar birth and death. Because they are forming so many massive stars simultaneously, these galaxies also experience a correspondingly high rate of core collapse supernova. It's a chain reaction of cosmic violence. The birth of many massive stars leads inevitably to a high frequency of their explosive deaths. This creates an environment where the energy from these successive explosions doesn't just dissipate quietly into space. It begins to add up, creating a collective, galaxy-wide effect that can fundamentally reshape the entire system. This cumulative energy input leads to one of the most important large-scale phenomena in galactic evolution, the galactic wind. Imagine a single supernova blast wave expanding into space. Now imagine dozens or even hundreds of these shockwaves occurring in relatively quick succession within the same region. These individual bubbles of hot, expanding gas begin to merge and overlap, creating a vast, superheated cavity of plasma. The pressure inside this cavity becomes so immense that it can no longer be contained by the galaxy's own gravity. This pressurized gas then bursts out, flowing from the galaxy's disk in a bipolar fountain, carrying with it vast quantities of heavy elements and raw star-forming fuel. This is a galactic wind, a torrent of material being driven out of the galaxy itself, a direct result of the collective fury of its most massive stars living and dying in quick succession. The consequences of these winds are profound and twofold. In the short term, they act as a powerful self-regulation mechanism for the galaxy. By ejecting the very gas and dust that would otherwise collapse to form the next generation of stars, the wind effectively starves the galaxy of its future fuel. It's a cosmic case of a boom leading to a bust. The incredible starburst, fueled by a rich reservoir of gas, ultimately sows the seeds of its own demise by triggering the winds that will blow that gas away. This process naturally limits the duration of these intense star-forming episodes, preventing the galaxy from burning through all its material at once and potentially explaining why we don't see many middle-aged galaxies with such extreme characteristics. In the long term, however, these winds are crucial for the chemical enrichment of the entire cosmos. The material driven out by these galactic fountains doesn't just disappear. It is injected into the vast, near-empty spaces between galaxies, a region known as the intergalactic medium. This ejected material is rich with heavy elements forged in the hearts of those short-lived massive stars and scattered by their supernova. Through this process, starburst galaxies and their energetic winds act as the primary distributors of elements like oxygen, carbon, and iron throughout the universe. They pollute the pristine intergalactic void, ensuring that when the next generation of galaxies forms from this enriched gas, they will already possess the heavy elements necessary to form rocky planets and potentially life. The frantic activity within a tiny green pea galaxy, therefore, has implications that reach across millions of light years, contributing to a grand cycle of matter that connects the fate of all galaxies. While the expanding shells of supernova remnants create some of the most beautiful structures in the cosmos, they are also home to something far more potent and invisible. They are the primary particle accelerators of our galaxy. This brings us to a phenomenon that directly connects these titanic explosions to our own planet. We are constantly, every second of every day, being bombarded by high-energy particles from space. This invisible rain is known as cosmic rays, and for over a century, the origin of the most energetic ones has been one of astronomy's great puzzles. We now have compelling evidence that the source of most of these galactic cosmic rays is not some mysterious dark object, but the immense expanding shock waves from supernova remnants. To understand how this works, picture the outer edge of a supernova remnant, a shell of gas and magnetic fields expanding into the interstellar medium at thousands of kilometers per second. This is not a gentle push, it's a supersonic shock front, a cosmic sonic boom of immense power. Now imagine a single charged particle, a proton or an atomic nucleus wandering through space. It gets caught up in this turbulent, magnetized environment. The key to the whole process is that the shock wave is moving so fast that the space ahead of it and behind it are like two different realms. The particle, trapped by the magnetic fields, bounces back and forth across this shock front. Each time it crosses from the slower-moving, turbulent region behind the shock into the fast-moving flow ahead of it, it gets a boost of energy like a surfer catching a wave over and over again. This mechanism, known as Fermi acceleration after the physicist Enrico Fermi who first proposed it, allows particles to be whipped up to velocities approaching the speed of light. The supernova shock acts as a natural and incredibly efficient cosmic cyclotron. With every crossing, the particle gains a little more speed, being reflected by magnetic irregularities on either side of the shock. It's as if the particle is in a magnetic ping-pong game where the paddles are moving, and with every volley, the ball gets faster and faster. This process can continue for thousands of years, gradually building up the energy of these particles until they become the ultra-high-energy cosmic rays we detect. The sheer size and longevity of a supernova remnant provide both the space and the time for this acceleration to occur, creating a natural particle accelerator far more powerful than anything we could ever build on Earth. The expanding shell essentially acts as a giant magnetic trap, confining these particles and forcing them to ride the shock wave until they eventually escape into the galaxy. The evidence for this theory is now overwhelming, thanks in large part to our ability to observe the universe in gamma rays. When these accelerated cosmic rays, which are primarily protons, collide with the slower-moving atoms of gas in the interstellar medium, the interaction produces subatomic particles called pions. These neutral pions then almost immediately decay into pairs of high-energy gamma-ray photons. Therefore, by detecting a telltale glow of gamma rays emanating from a supernova remnant, astronomers are effectively seeing the signature of this violent particle acceleration process in action. It's the direct, observational proof that these remnants are indeed the factories that produce the cosmic rays which permeate our galaxy. Telescopes like the Fermi Gamma Ray Space Telescope have mapped this emission from numerous remnants, creating a clear and convincing picture that ties these ancient explosions to the high-energy particles that constantly sleet through our solar system. This creates a profound and tangible link between the most energetic events in the galaxy and our own world. Those cosmic rays, born in the fury of a stellar cataclysm thousands of light years away, are not just an abstract concept. When they reach Earth, they collide with atoms in our upper atmosphere, creating showers of secondary particles that cascade downward. Some of these particles are the muons that pass harmlessly through our bodies and the ground beneath our feet every second. They are also responsible for the occasional bit of random noise in our electronic devices and even contribute a small portion of our planet's natural background radiation. So, the next time you use a device with a semiconductor, a tiny fraction of the errors it might experience could be traced back to a particle that was accelerated in the magnetic maelstrom of a supernova shock wave. It's a humbling reminder that we are not isolated from the galaxy's violent events. We are physically connected to them by an invisible, energetic rain that has been traveling for centuries, a direct messenger from the death of a star. After exploring the spectacular, violent deaths of stellar giants, it's natural to look up at our own sun and wonder about its ultimate fate. The reassuring news is that our sun will never experience a supernova. The cataclysmic explosions we've been discussing are reserved for stars at least 8 times more massive than our own. Our sun, a relatively modest star, is destined for a far more gentle and drawn-out transformation, one that will fundamentally change our solar system but lacks the instantaneous, galaxy-shaking violence of a supernova. Our sun's future is written in its mass. For the past 4.6 billion years, it has been steadily fusing hydrogen into helium in its core, a stable process that provides the light and heat that makes life on Earth possible. This will continue for another 5 billion years or so. However, the core will eventually begin to run out of hydrogen fuel. When this happens, the delicate balance between the outward pressure of fusion and the inward crush of gravity will be disrupted. Without the energy from hydrogen fusion to support it, the core will start to contract under its own weight. This contraction, however, has a dramatic side effect. It heats up the surrounding shell of hydrogen, which then ignites in a shell of fusion around the inert helium core. This massive influx of new energy causes the Sun's outer layers to expand enormously, and it will swell into what is known as a red giant. This red giant phase will be the beginning of the end for the inner solar system. The Sun will expand to a colossal size, its outer atmosphere stretching outwards until it likely engulfs the orbits of Mercury and Venus. Earth's fate hangs in the balance. While it's possible our planet's orbit could migrate outward slightly as the Sun loses mass, the most likely scenario is that Earth will be swallowed by the Sun's tenuous but incredibly hot outer layers. The planet will be vaporized, its substance becoming one with the star that gave it birth. For a brief cosmic moment, the Sun will be 100 times wider and thousands of times brighter than it is today, a magnificent red orb dominating the sky of any surviving outer worlds. But this immense, distended state is unstable. The core, now composed of helium, continues to contract and heat up until it reaches a temperature of around 100 million degrees, hot enough to ignite helium fusion in a violent event known as the helium flash. This fuses helium into carbon and oxygen. However, our Sun's core will never get hot enough to fuse carbon. This is the critical fork in the road. In a more massive star, carbon fusion would begin, leading further down the path to an iron core and a supernova. For our Sun, the fusion journey ends with carbon and oxygen. After a period of instability where it may puff off its outer layers in a series of pulses, the Sun will finally shrug off its entire outer envelope, creating a beautiful, glowing shell of gas known as a planetary nebula. What remains after this final act of shedding will be the Sun's exposed core, a white-hot, Earth-sized ember known as a white dwarf. This object, with a mass roughly half of what the Sun has now, will be compressed into a volume 1,000,000 times smaller. A single teaspoon of white dwarf material would weigh as much as an elephant here on Earth. This incredible density is supported by a quantum mechanical force called electron degeneracy pressure, the same force that prevents a white dwarf from collapsing further. It will no longer undergo fusion. It is simply the fading, super-dense corpse of a star, initially blazing with leftover heat at temperatures of over 100,000 degrees. Over billions of years, this white dwarf will slowly cool and fade, eventually becoming a cold, dark, crystalline object known as a black dwarf, the final, silent end of a star like our Sun. This peaceful fate stands in stark contrast to the dramatic ends of the massive stars we have discussed. A star like Betelgeuse, which could go supernova at any time in the next 100,000 years, will leave behind a neutron star or a black hole. Our Sun will leave behind a white dwarf, a dense cinder embedded within the beautiful, expanding cloud of its planetary nebula. These different outcomes illustrate a fundamental rule of stellar evolution: mass is destiny. The initial mass of a star dictates its temperature, its luminosity, its lifespan, and ultimately the manner of its death. Our Sun's quiet demise is the most common fate for stars in our galaxy, a testament to the fact that while the universe is capable of unimaginable violence, it also allows for a slow, graceful, and beautiful exit for the vast majority of its stellar inhabitants. But here's a cosmic puzzle that has astronomers scratching their heads. Despite knowing how many massive stars are born in galaxies like our own, we consistently observe fewer core collapse supernovae than our models predict. It's as if a significant number of these stellar giants are simply vanishing without their final, brilliant farewell. This discrepancy is known as the missing supernova problem, and it points to a fundamental gap in our understanding of how the most massive stars actually die. The universe, it seems, has a way for stars to cheat the traditional explosive death, to disappear from the cosmic stage with nothing more than a quiet whimper. One of the most compelling solutions to this mystery involves a phenomenon as dramatic as it is invisible: the direct collapse into a black hole, an event sometimes called an unnova. Imagine a star so incredibly massive, perhaps 40, 50, or even 100 times the mass of our Sun, reaching the end of its life. In a standard core collapse supernova, the star's iron core implodes, rebounds, and creates a shockwave that blasts the outer layers into space. But for the true titans, the story might end differently. If the star is massive enough and has lost a significant portion of its outer hydrogen envelope, the core collapse might be so complete and the gravitational pull so overwhelming that the outgoing shockwave simply doesn't have the energy to overcome the tremendous infall of material. The shockwave forms, but it stalls and is quickly swallowed. There is no rebound, no brilliant flash of light, no expanding nebula. The entire star, core and all, simply implodes directly into a black hole. From the outside, the star would just wink out. It would vanish from the sky, leaving behind only the gravitational signature of a new black hole. This failed supernova or unnova is a stellar death that bypasses the explosion phase entirely, providing a perfect explanation for why we might be missing a large fraction of expected supernova. Another major factor cloaking these stellar deaths from our view is something far more mundane, yet incredibly effective: cosmic dust. The very same massive stars that end their lives in supernova often spend their final millennia in a phase of intense mass loss, blowing off their outer layers in powerful stellar winds. This ejected material, rich in heavy elements, can form a thick, opaque shroud of gas and dust around the dying star. When the supernova finally does occur, its light must first punch through this dense, pre-existing cocoon. The initial ultraviolet and optical flash can be almost completely absorbed by this dusty envelope. The energy isn't lost, it's reprocessed. The dust absorbs the high-energy light and re-radiates it as lower-energy, longer wavelength infrared light. So, what we might miss in our optical telescope surveys could be appearing as a brilliant but hidden infrared source. We are only just beginning to conduct large-scale, systematic infrared surveys of nearby galaxies, and they are already revealing these previously hidden supernovae, suggesting that a significant portion of the missing ones were simply cloaked in dust. The hunt for these elusive events is pushing the boundaries of observational astronomy. It requires a multi-wavelength approach, using instruments that can see through the dust in the infrared and that can detect the faint, high-energy signals that might escape a failed explosion. Some of the most exciting evidence comes from the sudden disappearance of stars. There are now a handful of documented cases where a star was visibly present in older astronomical images, but has since vanished without the traditional trace of a supernova. In one notable instance, a massive, unstable star in a galaxy over 20 million light-years away was monitored for a decade. It then dramatically faded in brightness over a period of just a few months and then disappeared entirely. The leading explanation is that it collapsed directly into a black hole. The fading could have been the final flicker of material falling onto the newborn black hole before the fuel source was cut off and the light was extinguished for good. This missing supernova problem forces us to reconsider the stellar life cycle. It suggests that the path a star takes in its final moments is not a simple binary choice between supernova or quiet white dwarf, but a nuanced spectrum of possibilities heavily influenced by its initial mass, rotation, and composition. The direct collapse scenario implies that a substantial number of black holes are being born in utter silence, without the brilliant electromagnetic fanfare we have come to associate with stellar death. This not only explains a statistical anomaly but also enriches our understanding of cosmic evolution, revealing that some of the universe's most dramatic transformations happen in the dark, hidden from our direct sight, yet fundamentally shaping the population of black holes and the distribution of elements throughout the cosmos. It's a humbling reminder that for all we have learned, the universe still holds onto secrets, allowing some stars to depart in the most secretive way imaginable. We have explored the brilliant light, the invisible particles, and the powerful shock waves of these cosmic explosions. But there is one more dimension to experience, one that connects with us on a deeply primal level. We are about to listen to the universe. Now, we all know the famous line from the movie Alien, "In space, no one can hear you scream." This is absolutely true in the literal sense. Sound, as we know it, requires a medium like air or water to travel through, molecules bumping into each other to create a pressure wave. The near-perfect vacuum of interstellar space has far too few particles for these pressure waves to propagate in any way our ears could detect. A supernova, for all its fury, would tear through a star system in profound, deafening silence. But what if we could use a different sense to hear the music of the spheres? This is where a fascinating scientific practice called data sonification comes into play. Sonification is the process of translating data numbers, measurements, patterns into sound. It's not about recording actual sound waves in space. It's about using pitch, volume, and rhythm to represent the ebbs and flows of information, turning a visual graph into an auditory experience. Think of a Geiger counter where the rapid clicking tells you about the intensity of radiation without you ever seeing a dial. Astronomers are now doing this with some of the most dramatic events in the cosmos, giving us a new, visceral way to connect with the data. Our ears can often detect subtle patterns and rhythms that our eyes might miss on a chart, making sonification both an artistic endeavor and a powerful analytical tool. So, what would a supernova sound like if we could sonify its key stages? Let's start from the very beginning, from the inside out. The first true scream of a dying star isn't light, it's that tremendous blast of neutrinos. Remember, this is the moment of core collapse, and the neutrino burst carries away a staggering amount of the star's energy. To sonify this, a scientist might assign a specific musical note to each neutrino detected. The initial collapse would be represented by a period of profound silence as the core implodes. Then, as the proto-neutron star forms and releases its flood of ghostly particles, the sound would erupt. It would be an impossibly dense, roaring crescendo of notes, all crashing together in a chaotic, blindingly fast torrent. It would last for just a few seconds, but in that time, the sound would represent more energy than any other single event in the star's death, a deafening, digital roar representing the birth cry of a neutron star, a sound no human ear could ever physically hear, but one we can now experience through the language of data. After that initial particle scream, the next act of the drama unfolds, the shock wave. We can sonify the expanding light curve of the supernova itself. Imagine taking the famous graph of a supernova's brightness over time. The horizontal axis, time, becomes the passage of our audio. The vertical axis, brightness, becomes pitch or volume. As the shockwave breaks through the star's surface and the supernova reaches its maximum brilliance, the sound would swell from a low, quiet hum into a soaring, brilliant tone that holds its peak for days or weeks. This would be the main theme of the explosion. Then, as the radioactive decay of nickel and cobalt takes over to keep the supernova glowing, the tone would begin to gradually, inexorably fall in both pitch and volume, fading over months into a deep, quiet thrum before finally disappearing into silence. This auditory timeline gives us an intuitive feel for the immense duration and energy of the event, far beyond what a static image can convey. Perhaps the most haunting sonification comes from the aftermath. Let's consider the beautiful, intricate structure of a supernova remnant like the Crab Nebula. Data from telescopes like the Chandra X-ray Observatory, which sees the incredibly hot gas, and the Hubble Space Telescope, which sees the delicate filaments, can be combined. In one such sonification, scientists assign different sounds to different components. The bright X-ray light from the central pulsar wind might be represented by a high, shimmering, continuous drone like a cosmic wind. The optical light from the expanding filamentary shell could be mapped to string-like plucked notes that form a complex, evolving melody. As your virtual position moves from the center of the remnant out towards the edges, the soundscape changes, creating a sound map of the structure. You are not just hearing an explosion, you are hearing the life of the nebula, the ongoing activity of its heart, and the slow, majestic expansion of its stellar tomb. It transforms a beautiful picture into a dynamic symphony, telling the story of creation from destruction. This process does more than just create captivating audio. It opens up the universe to people who are blind or have low vision, allowing them to experience the data and patterns of cosmic phenomena directly. It also offers scientists a novel way to analyze complex datasets. The human auditory system is exceptionally good at picking out subtle patterns, rhythms, and anomalies. A researcher listening to the sonified light curve of a distant star might notice a tiny, recurring dip in pitch that corresponds to a previously overlooked periodic dimming, hinting at the presence of an orbiting planet or a companion star. In the chaotic sound of a gamma ray burst's initial emission, a particular rhythm or structure in the notes might reveal details about the internal engine of the jet. By listening to the data, we can sometimes hear the secrets of the cosmos more clearly. So, while the vacuum of space will always be a silent frontier for our physical ears, our minds can now journey through a universe rich with sound. The cataclysmic death of a star, from its silent core collapse to its brilliant visual peak and its long, expanding aftermath, can be composed into a moving and powerful symphony. It is a reminder that our understanding of the universe is not limited to a single sense. By translating light into sound, we build another bridge between the human experience and the cosmic dance, allowing us to not just see the violence of the heavens, but to feel its rhythm and hear its incredible, silent song. It all started with a profound assumption, one that seemed so logical it was rarely questioned. For much of the 20th century, astronomers believed that while the universe was expanding, as Edwin Hubble had famously shown, the mutual gravitational pull of all the matter within it must be putting the brakes on that expansion. The big question wasn't if the expansion was slowing, but by how much. Two competing teams of scientists set out in the 1990s to measure this cosmic deceleration with unprecedented precision. They were both using the universe's ultimate mile markers, the remarkably consistent explosions of Type Ia supernova. These stellar events, which all detonate at nearly the same critical mass, shine with a predictable peak brightness, making them perfect standard candles. If you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its distance with incredible accuracy. These supernovae would act as the markers on the cosmic highway, allowing the teams to measure the expansion rate of the universe across vast stretches of time. The method was straightforward, but the results were anything but. The two groups, the Supernova Cosmology Project and the High-Z Supernova Search Team, were racing to collect data from the most distant supernova they could find. Because light takes time to travel, observing a supernova billions of light years away meant they were looking billions of years back into the past. By comparing the distance of these ancient supernovae to their redshift, a measure of how much the universe had stretched since the light was emitted, they could plot how the expansion rate had changed over cosmic history. The expectation was clear. The more distant, ancient supernova would appear brighter than expected because in a universe slowing down, the expansion was faster in the past, placing those supernovae closer to us than a constant expansion would suggest. They were fully prepared to measure just how much gravity was reigning in the cosmos. The data, however, told a completely different and shocking story. When the teams analyzed their observations, they found that the most distant supernovae were actually fainter than their models predicted. This was the complete opposite of what everyone expected. A fainter appearance meant these supernovae were farther away than anyone had calculated. For them to be so far, the expansion of the universe in the past must have been slower than it is today. There was only one possible, mind-bending conclusion. The expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was overcoming the collective gravity of all the galaxies, clusters, and dark matter, pushing the cosmos apart at an ever-increasing rate. It was as if you threw a ball into the air, and instead of falling back down, it shot away from you faster and faster into the sky. This discovery was so revolutionary and so counterintuitive that the teams spent years checking and rechecking their work, ruling out potential errors like intergalactic dust dimming the light or evolutionary changes in the supernova themselves. But the evidence was robust. The universe was undergoing accelerated expansion. This monumental finding, announced in 1998, sent shockwaves through the world of physics and astronomy. It demanded a radical explanation, and the one that emerged was as profound as it was mysterious: dark energy. This is not a substance in the traditional sense, but rather a property of space itself. The leading theory suggests that empty space is not nothing. It has an intrinsic, low-level energy density. As the universe expands, more space comes into existence, and with it, more of this repulsive energy. This is why the expansion accelerates. The push becomes stronger as the universe gets larger. The numbers involved are staggering. We now believe that dark energy makes up about 68% of the total mass energy content of the universe. Dark matter, another mysterious component, makes up about 27%, and everything we can actually see, all the stars, planets, gas, and dust, comprises less than 5% of the cosmos. The universe, it turns out, is dominated by forces and substances we cannot see and barely understand. The discovery that the cosmos is filled with this enigmatic force, all thanks to the precise light of exploding white dwarf stars, was recognized with the highest honor in science. In 2011, Saul Perlmutter of the Supernova Cosmology Project and Brian P. Schmidt and Adam G. Rees of the High Z Supernova Search Team were jointly awarded the Nobel Prize in Physics. Their work fundamentally altered our understanding of the universe's fate. Instead of a big crunch where gravity would eventually pull everything back together in a fiery collapse, the prevailing model now points toward a big freeze or heat death, where the relentless acceleration driven by dark energy will push galaxies apart until the universe becomes a cold, dark, and ever more lonely place. Yet, for all its monumental importance, dark energy remains one of the greatest unsolved puzzles in all of physics. We can observe its effects, but we have no idea what it actually is. Is it the cosmological constant that Albert Einstein first proposed and then famously discarded as his biggest blunder? Is it a dynamic energy field that has changed over time, known as quintessence? Or does its existence point to a fundamental flaw in our understanding of gravity, requiring a modification of Einstein's theory of general relativity on the largest scales? Every new observation of a distant Type Ia supernova, every new map of the large-scale structure of the universe, is another piece of data in this grand investigation. The legacy of these stellar explosions continues to shape the frontiers of knowledge, proving that the violent death of a star can illuminate not only the history of the cosmos, but also its ultimate destiny, forcing us to confront the profound mystery of the dark energy that governs it all. And just when we thought we had a handle on the different ways stars could die, the universe delivered a true head-scratcher. In June of 2018, a robotic telescope as part of the Atlas survey in Hawaii detected a sudden, brilliant flash in a galaxy 200 million light-years away. It was catalogued as a 2018 cow, and its random lettering quickly inspired the unforgettable nickname the Cow. At first glance, it seemed like it might be another supernova, but within days it became clear that this was something entirely new, something that defied every classification astronomers had painstakingly built over decades. The Cow didn't just challenge the rulebook, it set it on fire. The first bizarre clue was its incredible speed. A typical supernova takes weeks to climb to its peak brightness, like a slow-rising firework. The cow did the opposite. It exploded into view with breathtaking haste, achieving its blinding peak in just a matter of days. This wasn't a slow crescendo, it was a sudden, violent scream of light. And what a scream it was! At its peak, the cow was shining with the luminosity of 100 billion suns, outshining its entire host galaxy. But this brilliance was shockingly short-lived. Just as quickly as it appeared, it began to fade. Within a month, most of its light had vanished, whereas a supernova of comparable brightness would still be shining strongly for many months. This rapid rise and fall was the first major sign that the physics powering this event were fundamentally different from anything we had seen before. Then there was the strange composition of its light. When astronomers took its spectrum, the fingerprint that reveals the chemical elements present, they expected to see the telltale signatures of a star's outer layers, like hydrogen and helium, being blasted outward. Instead, the cow's spectrum was almost completely featureless. It was a smooth, hot, and blindingly blue continuum of light, as if they were looking at a massive, dense, and incredibly hot ball of plasma with no clear identity. This suggested that the material ejected in the explosion was both extremely hot and remarkably transparent, allowing us to see deep into the heart of the cataclysm in a way that isn't usually possible with the opaque ejecta of a standard supernova. It was like seeing the bright, white-hot element inside a light bulb, rather than the frosted glass that normally diffuses the glow. So, what cosmic engine could possibly produce such a fast, hot, and brilliant flash? The leading theories are as dramatic as the event itself, centering on the birth of a black hole or the violent death of a star in a completely new context. One compelling idea is that the cow was a failed supernova that resulted in the direct formation of a black hole. In this scenario, a massive star, perhaps a blue supergiant, underwent core collapse. But instead of producing a successful shockwave that blows the star apart, the explosion faltered. The shockwave stalled, and the core collapsed directly into a black hole. This newborn black hole wouldn't just sit there quietly. It would immediately begin to feast on the star's own inner layers, which were now raining down upon it. The incredible gravitational energy released by this stellar cannibalism, as material swirled into a frenzied accretion disk, would have powered the brilliant, fast-lived flash we observed. The cow in this model was the real-time birth cry of a black hole, a brief flare of intense light as it consumed its first meal. Another fascinating possibility involves a stellar tidal disruption event, but with a twist. Perhaps the cow wasn't the death of a single, isolated star, but the violent shredding of a white dwarf star by a black hole. A white dwarf, the dense Earth-sized remnant of a sun-like star, wandering too close to an intermediate mass black hole would be torn apart by immense tidal forces. The disruption of such a dense object, as opposed to a more fluffy main sequence star, could produce a much faster, hotter, and more energetic flare, matching the cow's unique properties almost perfectly. This would be a stellar death by dismemberment, a catastrophic encounter that vaporizes a stellar corpse in a final, brilliant act. What makes the cow and other fast blue optical transients like it so important is that they force us to acknowledge the gaps in our understanding. For a long time, astronomy had neat categories: supernova, kilonova, gamma-ray burst. The cow showed us that there is a whole zoo of exotic, transitional explosions happening in the cosmic shadows. It demonstrated that the process of a star's death is not a simple either-or proposition, but a rich spectrum of possibilities governed by mass, rotation, magnetic fields, and environment. The event was so unprecedented that it required a whole new classification, proving that our map of the cosmos is still filled with blank spaces marked "Here be monsters." These mysterious transients are the frontiers of astrophysics, pushing our telescopes and our theories to their limits as we strive to understand the full, violent repertoire of stellar death. But to truly appreciate where we are headed, you have to understand the fundamental shift happening right now in astronomy. For centuries, we have been passive observers of light. We built telescopes to collect the photons that happen to rain down on our little planet, piecing together the cosmos from this single, fleeting signal. But we are on the cusp of a revolution, one that will see us not just as watchers of the sky, but as listeners and feelers of the universe. We are entering the era of multi-messenger astronomy, where we combine the ancient sense of sight with the new senses of touch through gravitational waves and even smell through the detection of ghostly neutrinos. And the tools that will usher in this new age are already being built, promising to transform our understanding of cosmic explosions from a series of brilliant snapshots into a rich, immersive, multi-sensory experience. Leading this charge from the ground is an absolute powerhouse of a telescope, the Vera-C Rubin Observatory. Perched on a mountaintop in Chile, this facility is not like the telescopes that painstakingly study a single galaxy for hours. Think of it instead as the ultimate cosmic surveillance camera. Its primary job is to take an enormous, detailed picture of the entire southern sky not once, but over and over again every few nights. Its camera is so vast that a single image would require over 1,500 high-definition television screens to display. This relentless scanning will create an unprecedented motion picture of the universe, and in that film, transient events, things that change, blink, or explode, will be the stars. The Rubin Observatory is predicted to discover an almost incomprehensible number of new supernovae. Not dozens, not hundreds, but millions over its 10-year survey. It will find them in their very infancy, catching the shockwave as it first breaks through the star's surface, giving us a real-time window into the earliest moments of stellar death that we have ever had. It won't just find the ordinary ones. Its immense volume will allow it to capture the rarest of the rare, those mysterious superluminous supernovae, the perplexing fast blue optical transients like the cow, and perhaps entirely new classes of explosions we haven't even dreamed of yet. It will provide the context, showing us the exact galaxy and stellar environment each explosion came from, turning anonymous flashes into events with a rich backstory. While the Rubin Observatory scans the sky in visible light, a revolutionary mission is being prepared to listen to the universe from the quiet of space. Meet the Laser Interferometer Space Antenna, or LISA. This is not a telescope in any traditional sense. It will be a constellation of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers. Its purpose is to detect the ripples in spacetime itself, gravitational waves. The ground-based LIGO detectors made history by hearing the collisions of black holes and neutron stars, but they are limited to hearing only the highest-pitched cosmic events, the final frantic milliseconds before a merger. LISA will be tuned to a much lower frequency, allowing it to hear the cosmic symphony building for years, even decades, before the final crescendo. Imagine being able to listen to a pair of neutron stars, these ultra-dense stellar corpses, as they spiral closer and closer together over millions of years. LISA will detect their orbital dance long before they finally collide. It will give us a prediction, a cosmic forecast that a spectacular kilonova and a short gamma-ray burst will occur in a specific part of the sky at a specific future time. This is perhaps the most profound capability LISA will offer, the power of prediction. This is where the magic of multi-messenger astronomy reaches its full potential. Picture this: for years, LISA has been listening to the ever louder gravitational wave hum from a pair of neutron stars in a distant galaxy. The signal tells us their exact orbit and allows us to calculate that they will merge in exactly 1 month. Astronomers around the world are alerted. Every major telescope, from the Rubin Observatory on the ground to the James Webb and Hubble telescopes in space, is pointed at that predicted patch of sky, waiting. Then, right on schedule, the event unfolds. First, LIGO and other ground-based detectors pick up the high-frequency chirp as the stars make their final orbits and smash together. Almost simultaneously, space telescopes like Fermi and Swift detect the short, brilliant flash of a gamma-ray burst. Then, the optical and infrared telescopes see it, the brilliant, reddening glow of a kilonova, the cosmic forge where gold, platinum, and other heavy elements are being created in real time. By combining the gravitational wave signal that tells us the masses of the objects with the light signature that reveals the chemistry of the explosion, we get a complete picture of the event. We are no longer just watching a light show, we are feeling the vibrations of space-time and seeing the creation of elements all at the same time. This holistic view will answer fundamental questions about the nature of matter itself, precisely measuring how much gold is produced in a single merger and confirming the origin of the heaviest elements in our universe. The synergy between these new observatories will transform our entire approach. The Rubin Observatory, with its countless new discoveries, will act as a tireless spotter, flagging interesting and unusual explosions for other telescopes to study in detail. LISA, with its predictive power, will give the entire astronomical community a front-row seat to the most dramatic stellar deaths imaginable. But the network doesn't stop there. New instruments like the Square Kilometre Array, a colossal radio telescope, will map the aftermath of these explosions in unprecedented detail, while next-generation neutrino detectors will catch the very first particles to escape a collapsing stellar core. We are building a global and even solar system-wide nervous system for sensing the cosmos. This integrated approach will allow us to finally solve long-standing mysteries like the missing supernova problem by perhaps hearing the gravitational wave thud of a direct collapse to a black hole even when no light is emitted. It will let us test the limits of general relativity in the strongest gravitational fields and probe the very first seconds of the universe by listening for the gravitational wave background from the Big Bang itself. We are moving from an era of observing the universe to an era of experiencing it with every sense at our disposal, a journey that will undoubtedly reveal wonders beyond our current imagination. And so, after this incredible journey through the universe's most violent and creative forces, we arrive at a modern-day record breaker, an event so colossal it reset the scale for what we thought was possible. On the 9th of October 2022, wave after wave of high-energy radiation began washing over our solar system. It originated from a point in the constellation Sagitta, the Arrow, and it was a signal that immediately sent automated alerts flashing across astronomers' screens worldwide. This was JRB 221009A, and it would soon earn itself a legendary nickname, the BOAT, the brightest of all time. It was not a subtle event. The initial pulse of gamma rays was so phenomenally intense that it completely saturated the detectors on nearly every gamma ray telescope in space, effectively blinding them. Instruments on spacecraft like Swift and Fermi, designed specifically to study these bursts, were momentarily overwhelmed, their readings driven off scale by the sheer deluge of energy. This single gamma-ray burst, originating from a galaxy nearly 2 billion light-years away, was, for those few hundred seconds, the most luminous object ever recorded in the known universe, outshining the combined light of every star in every galaxy its radiation passed on its long journey to us. To truly grasp the scale of the BOAT, let's put some numbers to its fury. A typical long gamma-ray burst is already a staggering event, releasing more energy in a few seconds than our Sun will over its entire 10 billion-year life. GRB 221009 was in a league of its own. Based on the data that wasn't saturated, astronomers calculated that it was roughly 70 times brighter than the previous record holder. The total energy it released across all wavelengths was immense. But what made it truly special was the energy contained in its highest energy photons. For the first time, we detected gamma rays with energies exceeding 10 tera-electronvolts. To understand that, you need to know that 1 tera-electronvolt is 1 trillion electronvolts. The most powerful particle accelerator on Earth, the Large Hadron Collider, smashes protons together at energies of about 13 trillion electron volts. The photons from this gamma-ray burst had energies comparable to the particles we create in our most advanced machines, but they were produced naturally 2 billion light-years away, and they traveled across the cosmos to land in our detectors. This single observation pushed our understanding of the physical processes at work within these jets, proving they are even more efficient particle accelerators than our most optimistic models had predicted. The cause of this unprecedented brilliance is believed to be the textbook collapse of a truly monstrous star directly into a black hole, a hypernova on steroids. The data points to a collapsar model where the progenitor star was likely incredibly massive, spinning rapidly, and possessed a relatively low metal content, all factors that can contribute to creating an exceptionally powerful and focused jet. The remarkable brightness we observed, however, was not just a product of the engine's raw power, but also a fortunate, or perhaps unfortunate alignment of cosmic geometry. As we've learned, the energy of a gamma-ray burst is not emitted in a sphere, but is concentrated into two narrow, relativistic jets. For the BOT to appear so phenomenally bright to us, our solar system must have been looking almost directly down the barrel of one of these jets, within a few degrees of its central axis. This rare alignment gave us a perfect, head-on view of the cosmic cannon, maximizing the intensity of the radiation we received and granting us a pristine view of the inner workings of this stellar catastrophe. The legacy of the BOT extends far beyond just setting a new record. Its extraordinary brightness acted as a brilliant cosmic flashlight, illuminating its own path through the universe. As the initial blast faded, the resulting afterglow was studied by over 20 telescopes across the electromagnetic spectrum, from radio waves to the highest energy gamma rays. This rich, multi-wavelength dataset provided an unparalleled look at the interaction between the ultra-relativistic jet and the environment surrounding the dead star. The light from the afterglow revealed details about the density of the circumstellar material, the structure of the magnetic fields within the jet, and the mechanisms that accelerate particles to such incredible speeds. It was a natural laboratory for extreme physics, offering insights that we could never replicate on Earth. Ultimately, the detection of GRB 221009 serves as a powerful and humbling reminder. It proves that even with our sophisticated models and advanced technology, the universe is still capable of producing phenomena that push the very boundaries of our theories. The BOT was not just an outlier, it was a signpost pointing toward the existence of an even more extreme population of stellar deaths that we have only just begun to sample. Every time we witness such an event, we are not just watching a distant star die. We are calibrating our understanding of the fundamental laws of physics under conditions of unimaginable energy and density. This single, brilliant flash from the depths of space continues to challenge and inspire, a definitive demonstration that in the cosmos, the brightest chapters in the story of destruction are often the ones that illuminate the path to deeper understanding. And so, our journey through 30 astonishing facts about the universe's most energetic explosions draws to a close, a voyage that has taken us from the brilliant death throes of supernova to the colliding corpses of neutron stars and the focused, universe-shattering fury of gamma-ray bursts. We have witnessed how these events are not merely destructive in points, but are, in fact, the fundamental engines of cosmic evolution. Every breath you take is filled with oxygen forged in a massive star, and every beat of your heart is powered by iron created in a stellar core just before it collapsed. The gold in a wedding ring and the platinum in a catalytic converter are literal stardust, forged in the violent embrace of a kilonova and scattered across the galaxy to one day become part of our world. These cataclysms are the great recyclers, the architects of complexity, transforming the simple hydrogen and helium of the early universe into the rich tapestry of elements that make planets, oceans, and life itself possible. This narrative reveals a universe of breathtaking violence and profound beauty, where the line between creation and destruction is beautifully blurred. A supernova remnant like the Crab Nebula is not just a tombstone, it is a stellar nursery in its own right, its shockwaves compressing nearby gas clouds to trigger the birth of a new generation of stars. The incomprehensible power of a hypernova, capable of birthing a black hole, also serves to seed the cosmos with the heaviest elements, while the magnetic fury of a magnetar reminds us that the universe is filled with forces beyond our everyday experience. Even the mysterious, fleeting flashes of events like fast blue optical transients challenge our categories and push us to develop new understandings of stellar death. From the precise standard candle of a Type Ia supernova that unveiled dark energy to the historic multi-messenger observation of a neutron-star merger, these explosions are not just celestial spectacles, they are our most powerful tools for probing the fundamental laws of physics and the history of everything. Ultimately, this story is our story. We are not just observers of the cosmos, we are a product of it. The calcium in our bones, the phosphorus in our DNA, and the carbon that forms the backbone of our very biology were all synthesized in the hearts of stars that lived and died long before our sun was born. We are the universe become conscious, looking back at itself and beginning to understand its own violent and creative history. The next time you find yourself under a clear, dark sky, take a moment to truly look up. That apparent emptiness is an illusion. Hidden within the darkness between the stars is a dynamic, ever-changing cosmos where titanic forces are constantly at work. A star may be dying in a glorious supernova in a distant galaxy, or two neutron stars may be spiraling toward a cataclysmic merger that will forge future worlds. Let that knowledge fill you with a sense of wonder and connection. The universe is not a static painting. It is a living, breathing, and yes, violently beautiful entity, and we are an intimate part of its grand, ongoing story. We would love to hear which of these cosmic explosions captured your imagination the most. Was it the stellar zombie of a magnetar, the golden alchemy of a kilonova, or the sheer raw power of the BOAT? Share your favorite fact or any questions you have in the comments below. And as always, thank you for exploring the incredible violence and beauty